GCE Advanced Level Chemistry Practical Series Experiment number 41, Preparation of a soap sample in the lab. Aim of this experiment is to learn the skills required for soap production under laboratory conditions. Now students, if you are taking a look at the introduction over here, we learned that this soap manufacturing process is also referred to as saponification process, and it dates back to about 600 BC. And we're using fatty acids such as palmitic, lauric, myristic, and these fatty acids are found in fat, basically animal fat, and vegetable oils. And in animal fat and in vegetable oils, what we mainly find is triglycerides. So we have mentioned that here fat and vegetable oils are basically triglycerides, and saponification process is the hydrolysis of an ester to produce a carboxylic acid salt and alcohol using a base as a catalyst. Now students, we have plant oils that we obtain. Actually, majority of the time soaps are made with the use of plant oils or vegetable oils. So these oils mainly contain triglycerides, and in the presence of a base, they can undergo alkaline hydrolysis, which will result in formation of a sodium salt of a long chain fatty acid. Or if you use potassium hydroxide as the base, you will end up forming potassium salt of a long chain fatty acid. So that process of breaking the triglyceride and forming these long chain fatty acid salts, sodium or potassium salts, are referred to as the saponification process. For soap production, both sodium and potassium hydroxide can be used. Because of that, soap can be generally called sodium or potassium salts of long chain fatty acids. Sodium or potassium salts of long chain fatty acids. When soap is dissolved in water, hydrolysis occurs to some extent to produce long chain carboxylic acids. Now that is a minute detail that will benefit you if you keep that detail in mind. Now what we are introducing into water when we are dissolving soap in water is basically a long chain fatty acids salt. So they will undergo dissociation and will form the fatty acid anion and sodium 1+ ion. So this fatty acid anion can again undergo a reaction to form the fatty acid, but this percentage of formation of this entire fatty acid is going to be very minute. You wouldn't form a lot of these fatty acids as these are weak acids. Apart from that, in the presence of calcium or magnesium 2+ ions, water-soluble soap can be converted into water-insoluble forms. Now this is why when it comes to washing yourself with hard water with the use of soap, or if you have ever washed your hands using water, using soap and hard water, you would have noticed the washing action is not clearly seen. Now this is because students, again as I mentioned earlier, in the presence of calcium and magnesium 2+ ions, the soap that we have is going to be turned into an insoluble form. We also say formation of soap scum takes place, and due to a precipitate that is formed, soap will no longer carry out its washing action. So this can reduce cleaning action of soap. So while keeping that in mind, we can now move on to this is the introduction. We can now move on to the next part of this theory part. Precautions. Concentrated sodium hydroxide is extremely caustic and corrosive. So students, you should not be handling this without your personal protective equipment. So you should be wearing specially eye protection. Students must wear eye protection while performing this experiment. Apart from that, all the other personal protective equipment like lab coats, proper shoes and gloves should be worn when carrying out this experiment. The raw materials needed for soap is given below. we can take animal oils or plant oils, or animal fat or plant oils. Sodium hydroxide or potassium hydroxide can be used. Citric acid, phosphoric acid, and fatty acids in coconut oil. Concentrated sodium hydroxide, or also known as brine solution. Coloring agents, fragrances, preservatives, and fillers can be used in the manufacturing process of soap. Now, for manufacturing of soap, to carry out the saponification process, we can actually use plant oils or animal fat. So, all of them contain triglycerides. We can choose one of these sources and continue to carry out the saponification process. But first of all, we need the plant oil or the animal fat extracted, and to that we will be adding our base and carrying out the saponification process. So we have many sources here. You can see different plant oil sources are there. So with the use of different plants, you can obtain different types of oils, and they can be used for the soap manufacturing process. Also, animal fats, extracted animal fats, can also be used for the saponification process. So as the base, we are using sodium hydroxide or potassium hydroxide. So either one can be used in the saponification process. We have citric, phosphoric acid, and free fatty acids in coconut oils used here as well. So you have an example of phosphoric acid and citric acid given here. Citric acid can be found in citrus fruits. So apart from that, we have to use phosphoric acid as well. Now, apart from that, we'll be needing a concentrated sodium chloride solution, which is also referred to as a brine solution. You can see we have taken a lot of salt and we have dissolved it in a small volume of water, resulting in formation of a concentrated sodium chloride solution. Apart from this, keep in mind this has to be a saturated sodium chloride solution. So here what we have formed is referred to as a brine solution. So we will be needing that for our experiment here, or the practical here. Now we move on to an important theory part, triglycerides. Animal and plant fats are triglycerides. Now triglycerides are esters. Triglycerides are esters. That is why we are capable of carrying out a hydrolysis reaction in alkaline medium, and this results in forming of an alcohol and a sodium salt of the carboxylic acid. If we carried out an hydrolysis reaction in acidic medium, we would have formed an alcohol and a carboxylic acid. Since we are carrying out this reaction, saponification reaction is carried out in an alkaline medium, so therefore what happens is a alkaline hydrolysis of a ester bond. So therefore, students, basically you will form a alcohol, and apart from that you will be forming a carboxylic acid salt or sodium salt of a carboxylic acid. The structure of the triglycerides are shown below. You can see the structure of the triglyceride. You can see in this part we have our glycerol molecule reacting with a long chain of fatty acid, producing these ester linkages, right? So each of these is a ester linkage, and here R could be a long chain hydrocarbon section such as C11H23, C13H27, C15H31, C17H35. So you can see these R groups are very long chain carbon or alkyl groups. So that together with this carboxylic groups is what we call as fatty acids or long chain fatty acids. So over here, those long chain fatty acids have formed ester linkages with a glycerol molecule, resulting in formation of our triglyceride. So this is the structure of citric acid and phosphoric acid. We already looked at that earlier, but we can now very clearly see without any distractions what the structure of citric acid is. So you can see it has 3 carboxylic acid groups and a OH group. And this is the structure of phosphoric acid, and there are 3 hydrogens that can be removed from one phosphoric acid. Preparation of soap by the hydrolysis of triglycerides. When triglycerides found in plant oils or animal fats are hydrolyzed with the use of sodium hydroxide or potassium hydroxide, sodium or potassium salts of fatty acids are formed along with glycerol. Now I told you, if you take an ester and carry out hydrolysis. Now when we use the word hydrolysis, that means we are going to be breaking a bond with the use of water. So now we have the ester molecule. With the use of water, we are going to be breaking the ester link. So when you are talking about hydrolysis, usually there are 2 main types of hydrolysis. Hydrolysis in acidic medium as well as hydrolysis in alkaline medium. Now, when you carry out hydrolysis of an ester in acidic medium, what you get, like I mentioned earlier, is an alcohol and a carboxylic acid. But when you carry out hydrolysis in alkaline medium, you get the alcohol and a sodium or potassium salt. Based on the base you used, you get the sodium or potassium salt of a carboxylic acid. So students, here we have the alcohol that is getting formed is basically a triglyceride. You have 3 OH groups in each triglyceride molecule. Apart from that, the long chain fatty acids that were attached to the triglyceride is now turning into sodium or potassium salts of long chain fatty acids, and that is what is known as soap. So when you carry out this hydrolysis reaction with the use of sodium or potassium, you form 2 main products. One is commonly referred to as soap, the other one is glycerol. The sodium or potassium salts of fatty acids are known as soap. That is a very crucial piece of information. The sodium or potassium salts of fatty acids are known as soap. So some fatty acids that can easily be found in plant sources are given over here, such as lauric, myristic, palmitic, stearic acid. So these are acids that are usually commonly seen in plant oils, and since we are using plant oils to produce soap, these sodium or potassium soaps of these fatty acids are found in soap. So you can see over here, this carboxylic acid is present as a sodium salt of that particular fatty acid. So you can see soap could be a mixture of these sodium or potassium salts of these given fatty acids. So it will serve you well to remember the names of these fatty acids, because these fatty acids are the main fatty acids that are going to be found in plant oil sources. So therefore, they are going to be found in their salt form or sodium or potassium salt form in the soaps that we use. Soap is a mixture of the sodium salts of the aforementioned fatty acids. Plant oils and animal fat. In plant oils and animal fats, triglycerides formed when fatty acids react with glycerol can be seen. These are also esters. For example, if you take coconut oil, it is a triglyceride. It can also be known as a glyceride of fatty acids. This has ester bonds and therefore can be considered an ester. So as I mentioned earlier, triglycerides are formed when glycerol molecules react with long chain fatty acids, forming 3 ester linkage per glycerol molecule. So therefore, these are referred to as triglycerides, and then apart from that, each of these triglycerides are esters. That is why when we carry out this alkaline hydrolysis, we form the products we formed and the products we saw earlier. So you can see here, you have these long chain fatty acids, and we have glycerol. Each glycerol molecule has 3 OH groups, and when they react, you can see each of the hydrogens from the OH groups will be removed in the esterification process, and OH groups from each of the fatty acids will be removed, and they will join to form ester linkages as given over here. So each of these are ester linkages. Each of these are ester linkages. Right, so this is in fact an ester. So now we move on to the main steps of soap production. There are 4 main steps. We have saponification, and when we carry out saponification, there will be 2 main products formed. One is soap, the other one is glycerol, and then we have to remove the glycerol. We don't allow all of the glycerol to remain in water, or we don't allow all the glycerol to remain in soap. Actually, glycerol is a product with a higher value. We'll be removing the glycerol from the soap. And then we have purification to remove any impurities that is left in the soap that we have produced, and then the finishing process. Step 1, saponification. Saponification is a process where purified coconut oil reacts with solution of either sodium hydroxide or potassium hydroxide. Now students, we don't always have to take only coconut oil. You can take any plant or animal fat for this process. In fact, there are certain soaps that are out there in the market that are made with different types of plant oils. Right, so based on the plant oils they have used, the type or the composition of the soap that they have produced will change. So if you use coconut oil, we have to use coconut oil after purifying the coconut oil, so to make sure there are no other impurities there. So we have coconut oil reacted with sodium or potassium hydroxide. This mixture is heated to 70 degrees Celsius, and then caustic soda or sodium hydroxide is dissolved separately in water due to its exothermic nature, and then the reaction occurs at the interface of immiscible oil and aqueous solution of sodium hydroxide layers, resulting in the formation of glycerine and soap. The heat produced from neutralizing sodium hydroxide ensures uniform reaction throughout the mixture. Now students, you have a plant oil. Let's say we take coconut oil, and then we separately dissolve sodium hydroxide. Sodium hydroxide dissolving in water is an exothermic process. If you have ever dissolved sodium hydroxide in the lab, you would know sodium hydroxide doesn't easily dissolve in water. It takes a little while, but sodium hydroxide pellets don't easily dissolve in water, but sodium hydroxide is soluble in water, very soluble in water. You have to keep that in mind. Apart from that, students, when you dissolve sodium hydroxide in room temperature water, it will take some time for the pellet to dissolve. But as the pellet dissolves, the entire beaker is now at a new temperature due to the process of dissolving sodium hydroxide being exothermic, right? So we first form our sodium hydroxide solution and we will take our oil. Usually the system should be around at 70 degrees Celsius, and then we mix the two. Since oil and water does not mix, there will be 2 layers. So you have to facilitate the mixing of these 2 layers through stirring. So at the interface of the 2 immiscible mixtures, you will see the reaction taking place, or hydrolysis reaction taking place, resulting in formation of soap and glycerol. Now you can see around at 70 degrees Celsius we form sodium salts of long chain fatty acids, which is referred to as soap, and apart from that, glycerol will also be formed. What is seen above is the hydrolysis of an ester. Here, glycerol is produced as a byproduct. actually the main byproduct. So observe the reaction over here, students. We can see when the hydrolysis is carried out, each of these ester linkages will be broken, releasing the glycerol and the carboxylic acid group. But in this case, when the reaction takes place, the carboxylic acid section will turn into a sodium or a potassium salt of a carboxylic acid. Since we have used sodium hydroxide, the result is the obtaining of a sodium salt of a long chain fatty acid. Now the next step is removal of glycerol. Now after the saponification process, aqueous phase exhibits reduced basicity. Yes, students, after the saponification process, since some of the sodium hydroxide gets used up in the process, the basicity in the medium, aqueous medium, is slightly less. And glycerin and certain amount of soap have dissolved in the aqueous phase. The dissolved soap molecules ionize and establish an equilibrium. Yes, students. So when we have these two layers reacting, saponification process takes place and soap is formed apart from glycerin. Now the soap can dissolve in the water layer, right? So soap obviously dissolved in the water layer. Now soap, as you remember, is sodium salts of fatty acids. So when soap dissolves in the water layer, soap can get ionized and you will have the ionized form of the fatty acid dissolved in water. So some soap, certain amount of soap that is produced will get dissolved in water. Apart from that, some glycerine will also dissolve in water. Actually, dissolving of glycerine in water. Yes, over here you can see it increases the aqueous phase density. It increases the density of the aqueous phase. Now, these are the main two things that you can observe as soon as the soap is formed. So now we need to extract soap. Some of the soap is dissolved in the water or water that was found in the reaction mixture. We need to remove soap as a solid. So how can we do that? Now, when soap dissolves in water, they have this equilibrium between the carboxylic acid anion and the soap, original soap molecules we have formed. So when we add sodium chloride or brine solution into the mixture, now we can see carboxylic acid with the sodium forms the sodium salts of carboxylic acid, and then that ionizes to form carboxylic acid anion and sodium ion. So if I add brine solution into the medium, sodium ion concentration increases drastically, pushing this equilibrium towards the right hand side where the sodium salts of carboxylic acids get reformed. So therefore, the solubility of soap in water will decrease when we introduce a brine solution with high concentration of sodium chloride into the reaction mix. So students, that's what we have done here. We add brine solution to decrease the soap solubility, shifting the equilibrium forward and causing the soap molecules to separate. So this is why we use sodium chloride. So students, when the sodium ion concentration is increased, as I mentioned earlier, the reaction that favors the decrease of sodium ion concentration will take place more according to Laird-Chatelier's principle. So when we increase the sodium ion concentration, sodium ion will combine with the carboxylic acid anion and will turn into sodium salts of carboxylic acid anion more, decreasing the solubility of soap in water. So therefore, whatever the soap that was dissolved in water will now precipitate out as sodium salts of carboxylic acid, right? So if they dissolve in water, they will ionize to form carboxylate anion and sodium ion. But when we increase the sodium ion concentration, they will join together again and will precipitate as sodium salts of carboxylic acids. So apart from that, students, in the previous slide, since the aqueous layer now is almost free of any soap, mainly what aqueous phase is going to contain is glycerol. So we can remove the aqueous phase along with the glycerol to obtain glycerol separately. After separating crude soap from aqueous phase, the glycerine containing aqueous phase is removed. Pumping crude soap is facilitated by 70 degrees temperature and the water content in soap. The soap solution extracted from the reaction chamber containing glycerine serves as a valuable glycerine soap. Glycerine is removed to be used in different cosmetic and other products. A small amount of glycerine is left in the soap to preserve the soft and smooth texture of soap. So to preserve the moisture and the soft and smooth texture of soap, we leave a little bit of glycerine in the soap. Otherwise, students, apart from that, most of the glycerine that got produced in this process is removed, because glycerine is another valuable product, especially in the cosmetic industry. So therefore, students, we remove the glycerine that is formed, which can be used in other products. Purification process. Water and sodium chloride salts are present in soap. Apart from that, students, other impurities can also be present. For example, if you have left some sodium hydroxide in the medium, and if you have not separated the precipitate properly, including certain amount of water in the precipitate along with sodium hydroxide, some sodium hydroxide also can be present in water. And we intentionally left some glycerine also in the soap sample, so we have to keep that in mind. So water, sodium chloride salts are present in the soap, which is purified to a certain extent by removing glycerine. So when we remove glycerine, we have certified it to a certain extent. The wet soap with salt undergoes centrifugation, separating the aqueous salt solution from the soap. So students, now we have wet soap. It's crude soap at this moment. We haven't dried it. We still have some moisture or wetness in it. So as you know, if you have ever carried out the experiment, and when we carry out the experiment, you will see the nature of the precipitate or nature of soap that is initially formed. So it has a lot of water in it, as well as some glycerine in it. So the wet water or wet soap that is present over here is centrifuged, and heavier soap particles will get collected at the bottom, leaving behind whatever the less dense aqueous or glycerine particles move towards the upper end of the centrifugation tube. So separating aqueous salt solution from the soap. So soap can be easily separated out in this method. The sodium chloride content in the soap decreases to 0.5% weight wise. So basically, students, if you consider this process is one of the processes that removes majority of the water soluble impurities through centrifugation. The presence of caustic soda in soap can be harmful to users, potentially even causing severe skin and eye damage. Now, I told you, we leave, or when we carry out the saponification process, we use sodium hydroxide. So some amount of sodium hydroxide can still be there. We can't guarantee that all of the sodium hydroxide got neutralized when saponification process took place. Definitely, certain excess amount of sodium hydroxide was there in the medium. So that could end up in soap. Imagine we don't remove the sodium hydroxide in soap, it could end up in the final product, which would eventually be harmful to the user because it could cause severe skin and eye damage. If soap gets in your eye, it could also cause eye damage. So to neutralize any sodium hydroxide present, citric acid, phosphoric acid, or free fatty acids from coconut oils are used. Now, students, sodium hydroxide is a base. Any acid that we have mentioned over here can be used to neutralize the base. Now, we have citric acid over here and phosphoric acid over here. Each of them has 3 hydrogens that can be released when reacting with sodium hydroxide. So, they can neutralize sodium hydroxide through the reaction of through acid-base reactions. So now, students, if you use free fatty acids from coconut oil, one of the important observations here is, now when you take coconut oil, apart from coconut oils containing triglycerides, it can also contain, to a certain degree, some free fatty acids, long chain carboxylic acids. They are free, they are not directly linked to a glycerol molecule forming triglycerides. So there are certain number of free fatty acids or certain amount of free fatty acids in coconut oil. So if you take these free fatty acids from coconut oils and react with the excess sodium hydroxide that is present in soap, through the reaction what you form is again a sodium salt of fatty acid, which is basically soap. So when we use free fatty acids that are seen in coconut oil, through this neutralization, what you again form is soap. So this is a good way of removal of sodium hydroxide without adding different types of other chemicals, because this will result in formation of mainly again sodium salts of free fatty acids, which is referred to as soap. Now finishing, removing water from soap after salt removal is crucial. We need to remove water. We don't want water to remain in the soap that we have produced. To reduce the water content to 12%, the soap is heated to approximately 120 degrees Celsius and sprayed into low pressure zone as small droplets. So this ensures, now when we heat it up to a temperature like 120 degrees, which is above 100 degrees Celsius, and then we spray it to form small droplets, whatever the moisture that is entrapped in the soap will be removed through this process. As water vaporizes, absorbing heat, the droplet temperature decreases, the water vapor is removed, and the soap settles in the low pressure vessel. The dry soap is then separated. Finished soap is achieved by blending fillers, coloring, perfumes, and molded into shape. So students, in the industrial manufacturing process of soap, after this process, after spraying the soap and drying it with the use of a high temperature, we actually obtain a dried soap sample, which is not yet the end product. As you know, you don't get just a white color soap without any odor to your hands when you actually purchase a bar of soap. It is mixed then with other substances like fillers, like preservatives, or maybe even fragrances and colors. So you see in the market we have different types of soaps with different smelling soaps. Apart from that, different colored soaps as well. So then after that, after mixing them thoroughly with the soap that we have obtained, we can mold them into different shapes, as you can see over here, and then it will come out to the market after being packaged. So this is the process of manufacturing soap. And in the market, you would find different types of soap. These are examples of different types of soaps, and you can see there are different colors as well. Examples of some perfume soaps are given over here. Soaps with sandalwood, you can see over here. Jasmine, rose, lemon, cinnamon, and clove fragrances can be seen in the industry. So after obtaining our dried soap, we can mix the fragrances to these soaps. To produce these soap, perfumes are added. So in order to produce different types of soaps that have different fragrances, we will add different types of fragrances or perfumes into the soap. So I hope you are familiar with these different types of soaps that are seen in the market, and now we know how they are formed. Apart from this, you will also see soaps with different colors. To obtain different colors in soap, coloring agents are added. You might have seen yellow color soaps, red color soaps, even blue color soaps. So basically, when you initially manufacture soap, it is going to be white. So we obtain these different colors in soap by addition of different coloring agents. Contents of coconut oil. In coconut oil, we can find triglycerides of fatty acids as well as free fatty acids. So as I mentioned, students, in plant oils, you will find mainly triglycerides. Apart from that, there will be a small amount of free fatty acids as well. Now, when we say free fatty acids, those are basically long chain fatty acids that are not forming a triglyceride, that are just present in the oil as the long chain fatty acid itself. The fatty acid percentages that can be found in coconut oils is given in the table below. Now, when you talk about triglycerides, triglycerides are formed when fatty acids react with glycerol. So, the types of fatty acids that are found in triglycerides also vary based on the plant oil that you look at, and usually when you consider a plant oil, it's going to be a mix of different fatty acid triglycerides along with a mix of free fatty acids. So over here we have the different types of fatty acids that are seen in oils. Now these are not all free fatty acids. Some of these will be present in the triglyceride form. So now we have these fatty acids that are seen in coconut oil listed in the table. We have lauric, myristic, palmitic, stearic, and oleic acid. So you can see when it comes to coconut oil, lauric acid, which is the formula is given over here, C11 H23COOH. We have 44.5% lauric acid in coconut oil, and this is a saturated fatty acid. Now, when you say saturated acid, that means this carbon chain over here is saturated. The carbon chain over here is saturated. And then we have myristic acid, and the mass percentage of myristic acid is 14%, and you can see over here the formula of myristic acid. And this section, the carbon hydrogen section, or the main carbon chain part of the fatty acid, is saturated. And we have palmitic acid. The formula is C15H31COOH. Even in that, this C15H31 section of the acid is saturated, and it is present 8% of the time. And then we have stearic acid, 3%. The formula is given over here, C17H35, and this section is saturated. So you can see coconut oil contains many saturated fatty acids. Then we have oleic acid, which happens to be unsaturated, and the formula is C17H33COOH, and its percentage is 5 to 8%. So these are the main acids of fatty acids that are seen in coconut oil. So you need to remember these names. It will be helpful if you remember these names of the different types of fatty acids that are present in coconut oil. The purpose of the addition of brine solution. So students, earlier we discussed that we will be adding brine solution to precipitate out our soap that is dissolved in the aqueous layer. We mixed oil and sodium hydroxide, which is the aqueous layer, and when we mix these two to produce soap, some of the soap that is produced dissolved in the aqueous layer. So to extract this dissolved soap from the aqueous layer, we can add sodium hydroxide. So we say, since soap produced can dissolve in water, the equilibrium below will be established. So we have soap that is produced that is going to be dissolved in, let's say, water to produce RCOO minus and sodium 1 plus. So when we add brine solution to this aqueous medium, sodium 1 plus ion concentration will increase. At this point, the product of the numerical values of sodium 1 plus concentration and RCOO minus concentration will be greater than the solubility product of soap. Now students, you can see over here, or before we go over there, you can see when we increase sodium ion concentration, this equilibrium should shift to the left. Or if you explain it with the use of our solubility product, now we have solubility product of the soap that is given here symbolically. If we increase the concentration of sodium ions, if we increase the concentration of sodium 1 plus ions, then the numerical value of sodium ion concentration will increase, and the product, or when you multiply these two, the final answer that you get is going to be greater than the KSP value that is there for soap. So students, when the numerical value of the product is much greater than the KSP value, that indicates that the soap is going to precipitate. So that is what happens. So when you increase the sodium ion concentration by the addition of brine solution into the aqueous phase, the soap or solid form of soap will be present or will be produced. Actually, at this point, the soap that was dissolved in the aqueous medium will be removed as a precipitate. Due to this reason, addition of brine solution results in separating the RCOONA, basically soap, as a solid. Glycerine will remain in aqueous medium. So glycerine is still in the aqueous medium. It can't be removed by the addition of sodium chloride, but by the addition of sodium chloride to the aqueous phase of the reaction mixture, the soap that was produced and that has now dissolved in water can be removed back as a solid. So now, with that, we can move on to the next slide. Reasons for adding weak acid in the soap manufacturing process. So sodium hydroxide that is added into the medium can end up in the soap that was produced. So soap that was produced now as a precipitate is going to contain certain amount of excess sodium hydroxide. To remove this, we can add a weak acid. Because sodium hydroxide is a base, weak acid and the sodium hydroxide will react and will neutralize the sodium hydroxide that is present in soap. If you do not do this, as I mentioned earlier, the excess sodium hydroxide present in soap can cause skin damage or eye damage in the consumer. Right, so the soap that have higher concentration of sodium hydroxide can cause harm to skin and soft tissues in the eyes. To neutralize sodium hydroxide present, weak acids such as citric, phosphoric, or free fatty acids that can be found in coconut oil can be used. The TMF value in soap. This is also a very important topic. TMF value. TMF or total fatty matter. Total fatty matter signifies the complete quantity of fatty substances contained within soap. It signifies the complete quantity of fatty substances contained within the soap. It denotes the percentage of RCOONA within the soap cake or soap bar if you are talking about an individual bar. So within any given soap bar, you have to have a bit of a high TMF value, because TMF value indicates how much soap you actually have in your soap bar, because soap is basically our RCOONA, or in other words, soap is basically the sodium source of the acid we have in the soap, sodium source of fatty acids. So therefore, students, TMA value talks about the complete quantity of fatty substances contained within the soap, or in other words, percentage of soap within the soap bar. Typically, the TMF value of washing soap ranges from about 54 to 56%, with the remaining portion comprising of fillers, additives that enhance the cleansing effectiveness and coloration. Certain body soaps will have high TMF values that are as high as 76%. So students, if you take a soap bar that you use at home, it is not entirely made out of our RCOONA, or it is not entirely made of the sodium or potassium salts of fatty acids. The sodium or the potassium salt fatty acid content might be limited to 54 or 56%. The rest will be fillers or other types of additives to enhance cleansing, or fragrance particles, or coloring agents. So those are what is making up the rest of the percentage. So now students, you can see there are certain soaps that really have a high TMF value that will have a better washing or cleansing action. So majority of the soaps, other than the ones that have a really high TMF value like this, 76.5%, majority of the soaps will have a TMF value of around 54 to 56%. However, a drawback of soap lies in its inability to dissolve and lather effectively in hard water. Right? You might have seen, as I mentioned earlier, sometimes when you try to wash your hands or even carry out some sort of cleaning action with the use of soap, if the water you use is hard water, at that point you can see that there is no bubble formation. It doesn't carry out the washing action properly. In fact, it leaves behind a bit of a coating of a precipitate on your hand. So that would indicate that the soap has not dissolved well in water. Something present in water caused the soap to form a precipitate. So this issue arises due to the interaction of soap molecules with cations present in hard water, resulting in formation of precipitates. So these cations, calcium, magnesium, especially calcium and magnesium, and Fe2 present, etc., can cause the soap to form a precipitate. Now students, sodium salts of fatty acids are soluble in water to a certain degree, and then we have calcium and magnesium salts of fatty acids. They are not very soluble in water. So when you dissolve sodium salts of fatty acids in water and then add calcium or magnesium into water, magnesium and calcium ions into water, you will see the soap will precipitate. And this is the reason why we can't observe a formation of bubbles, or we can't see the proper washing action of soap in the presence of hard water. Lathering will not take place in the presence of hard water. Now when it comes to baby soap, which is also known as soft soap, when it comes to baby soap, we produce baby soap with the use of potassium hydroxide and not sodium hydroxide. In the manufacturing process of baby soap, potassium hydroxide is used instead of sodium hydroxide. Here, the potassium salts of fatty acids formed are known as baby soap. So, these soaps are less harsh on the skin. So, therefore, students, there is a preference when it comes to formation of baby soaps to go with potassium hydroxide as a base. So, when it comes to our alkaline hydrolysis process, instead of the use of sodium hydroxide, we use potassium hydroxide. The potassium salts of fatty acids are said to be more softer on the skin and therefore more suitable for the use of infants. So the process of manufacturing baby soap is given over here. You have triglycerides and we will add potassium hydroxide instead of sodium hydroxide, and what you form here is potassium salts of fatty acids. Potassium salts of fatty acids, which are considered to be known as baby soap or soft soap. Determining whether an aqueous soap solution is acidic or basic. We need to figure out whether a given soap solution is acidic or basic. Now we have a small amount of soap that we can obtain either by scraping commercially available soap bar, or we can even make our own soap now. But if you make our own soap, or if you make your own soap and try to carry out this experiment, it is important to make sure that the soap does not contain any excess sodium hydroxide, right? Because if you have excess sodium hydroxide in your soap, then this experiment will not work as planned. So, first of all, you can obtain soap. Commercially available soap is good for this experiment. So, we take a small amount of soap, dissolve it in water, and you obtain an aqueous soap solution. And then we can take a piece of red litmus added to soap solution. The red litmus turns blue. The red litmus turn blue. So what turns red litmus blue? A basic solution could turn red litmus blue. This indicates that the soap solution is basic. This indicates that the soap solution is basic. So you have an example over here. When pH paper is used to test the pH of the solution, we can observe that soap solution typically have a pH value ranging from around 9 to 10. This could be a bit of a high pH value. So soap solutions are definitely alkaline. Soap solutions are definitely alkaline. So if you want to observe the pH of the soap solution with the use of universal indicator, we can take a small portion of soap solution into a test tube and add around 3 drops of universal indicator. And when you do so, you will see, after adding universal indicator and shaking it, you will see a specific color in the solution. Then you can compare that color against the color range of the universal indicator, or this color guide or color chart is going to be provided with the universal indicator that you use. So you can use this color chart to figure out the pH of your soap solution. So it could be, when you test, the answer could be between 9 and 10. So over here as well, you can see this color is somewhat close to pH 9, right? So it could be between 9 and 10 as well. The reason for soap solutions to be basic. The reason for soap solutions to be basic. So now students, we know soap is sodium salt of carboxylic acid or sodium salt of fatty acid. We have been given sodium salts. We can see a sodium salt of fatty acid over here. R group is a long chain hydrocarbon chain, or which contains a large number of carbon atoms. So now you can see these fatty acid sodium salts, when they are dissolved in water, they can get ionized to form RCOO minus and Na1 plus. So again, this is a carboxylate anion. RCOO minus is a long chain fatty acid carboxylate anion. So basically, students, these anions or fatty acid anions can react with water in the aqueous medium and get protonated again, leaving behind an OH minus. So they can obtain one of the hydrogens from water and break water into forming OH minus. So this reaction forms a carboxylic acid along with OH minus. So students, this is the reason why the OH minus concentration in soap is, or in soap water or soap solutions, are going to be higher, resulting in a higher pH. So first, soap dissolves in water, forms these two ions. So one of the ions, the carboxylate ion over here, can react with water to produce carboxylic acid and OH minus ion. So OH minus contributes to increasing the pH of the aqueous phase. The reaction increases OH minus concentration in the medium. The acid formed here is a very weak acid. So this means the acid will not fully dissociate and release H plus into the medium. Therefore, H plus concentration in the medium will be smaller than the OH minus concentration in the medium. So just to give you an idea, again, if you go back over here, through this process, OH minus ion concentration increases. But the formed weak acid will not release all of the H plus that it took in the formation of this carboxylic acid. So students, although this produces a huge number of OH minus ions, the H plus that is produced by releasing the H plus from this carboxylic acid is minimal. So there is a net increase of the OH minus ions. This reaction increases OH minus concentration in the medium, and the acid that is formed here is a weak acid. This means the acid will not fully dissociate and release H plus into the medium. Therefore, H plus concentration in the medium will be smaller than the OH minus concentration in the medium. So students, this is why the pH will increase. As you can see here, when water dissociates water is used in this reaction, you produce the carboxylic acid and OH minus. As water gets used up, carboxylic acid and OH minus gets formed. And students, this will cause the OH minus concentration to increase, right? And the hydrogen over here is not easily released. Why? Because the carboxylic acid over here is a very weak acid. It will not fully dissociate. It will release H plus, but only a minute amount of H plus, or very small amount of H plus is going to be released through the dissociation of the carboxylic acid that is formed, right? So it will not, if it completely fully dissociates and releases all of the H plus, then H plus concentration coming into the medium through dissociation of the acid and the OH minus that is formed over here will be equal to one another. So therefore, there won't be any effect due to this reaction. However, when this reaction happens, there will be a certain amount of OH minus ions coming into the medium, and the H plus that will come into the medium due to the dissociation of the carboxylic acid will not be that high. Only a very small amount, or only a very small percentage of all of the carboxylic acid that is formed here will dissociate. Therefore, students, it will never be as high as the OH minus ions that got produced here. So there is an overall increase of the OH minus ion concentration, which results in an increase of the pH. So therefore, the H plus concentration in the medium will be much smaller than the OH minus ion concentration in the medium. So you can see soap solutions are blue, or turning red litmus to a blue color, indicating that it is definitely basic. The reason for soap to dissolve in water. Soap is a mixture of sodium salts or fatty acids. These soap molecules have a long carbon chain in them, right? So you can, as you can see, a long hydrocarbon chain connected to COONA part, right? So we have a massive carbon chain here that is indicated through this zigzag line. Now, as you know, hydrocarbon sections within a given organic molecule are usually non-polar. So this long chain of the hydrocarbon or long hydrocarbon chain that is present over here is mainly consisting of carbon and hydrogen atoms, and this section is going to be non-polar. It will not dissolve in polar solvents that well. So we call that the hydrophobic tail of the soap molecule. We say soap molecule has two ends. One end is the hydrophilic head and the other end is the hydrophobic tail. So hydrophobic tail is basically our hydrocarbon section of the water molecules or of the soap molecule. So this hydrocarbon section is referred to as the hydrophobic tail part of the soap molecule. We call it hydrophobic because it is non-polar and it will not dissolve well in polar solvents like water. So in water, this part is not very soluble. And then we have the hydrophilic head. Now in this region, first of all, this is charged, and charged particles dissolve well in what? Apart from that, these bonds are polarized. So this section dissolves well in water. So we call this area of the water soap molecule our hydrophilic head. So there are few examples of soap molecules. Now if you highlight just one, in any given soap molecule, this section is the hydrophilic part or polar section, and this part is our non-polar or hydrophobic section. So some examples of different soap molecules are given here. The structural formula of a soap molecule. So as I mentioned over here, earlier on we looked more or less of a small diagram of a water molecule. Here we have a structural formula of a soap molecule displayed. So each of these carbon-carbon bonds, they are non-polar, and carbon-hydrogen bonds, although there is an electronegativity difference between carbon and hydrogen atoms, they do not create a sufficient polarity. This main hydrocarbon section that we see over here is overall showing non-polar characteristics. So students, this part is not necessarily polar. It will not dissolve in polar solvents like water. Or solubility of these sections in polar solvents like water is minimal. So we have this hydrophobic tail, long hydrocarbon chain, soluble in oil, not very soluble in something polar like water. And then hydrophilic head. Hydrophilic head. It's short and it's an ionic section, so therefore it is charged, therefore it is soluble in water. So we call this hydrophilic section or hydrophilic head. We always refer to it as hydrophilic head, and we always refer to this as a hydrophobic tail. Now the structure is very important because when explaining the washing or cleaning action of soap, this knowledge will be very important. The hydrophilic or hydrophobic tail section of soap is made of long chain hydrocarbon section. This section is non-polar and is insoluble in water or relatively insoluble in water. However, it is soluble in non-polar substances like oil and grease. So non-polar things dissolve in non-polar things, or like dissolves like. In one end of soap molecule, a short ionic section can be found, this section is polar and can dissolve in water, as water is also a polar solvent. Therefore, it is referred to as the hydrophilic head of the soap molecule. Therefore, soap molecule consists of two main sections. Therefore, soap molecule consists of two main sections: hydrophilic head and hydrophobic tail. We have already observed this by now. So now, students, let's take a look at the washing action of soap. So when you take soap molecules, it has a hydrophobic tail and a hydrophilic head, right? So this section is our hydrophobic tail, and this is our hydrophilic head. And when we take a dirt particle, which is an oily or a greasy material. Now imagine this is an oil particle, right? So the soap molecules are capable of, or one end of the soap molecule is capable of dissolving in oil, while the other is capable of dissolving in water. So you can see the tail section of the soap molecule can dissolve in oil, and the head section of soap molecule can dissolve in water. So the entire oil droplet will be having soap molecules tail sections dissolving in it, exposing the head sections of soap molecule on the surface of the oil droplet, like so. So now oil, as you know, doesn't dissolve in water. That's why we can't wash oil with just water. But if you apply some soap, even after, let's say, you have lunch and certain amount of oil is now clinging onto your hands, and then if you want to wash off this oil, we use soap. If you just wash it off with water, you would notice that it doesn't get washed off. But when you use soap, it will wash off. The reason is the oil, first of all, will turn into oil droplets when you're trying to wash the oil from your hands. And these oil droplets are going to be, or the tail sections of soap is going to be dissolving in the oil droplet, exposing the hydrophilic head on the surface of the oil droplet. So from the exterior, you only see the hydrophilic heads of the soap around the oil droplet. So now imagine, although the oil droplet is not soluble in water, now the entire surface of the oil droplet is covered in hydrophilic heads. So this hydrophilic heads collectively can easily dissolve in water. Now, along with dissolving the hydrophilic heads, due to this entire oil droplet being completely covered by hydrophilic heads, even the oil droplet will dissolve in water. So students, because of that, oil can be washed off with the use of soap. Oil on itself will not interact with water and dissolve in water, but if the surface of the oil molecule, or not the oil molecule, surface of the oil droplet is completely covered with soap molecules, hydrophilic heads, due to hydrophilic heads dissolving in water, the entire oil droplet gets dissolved in water. So students, this is referred to as the washing action of soap. Due to this, oil droplets or other greasy material can be washed off with the use of soap. Formation of soaps come. When soap is dissolved in hard water, there will be no lathering of soap. Instead, a precipitate will be formed due to the formation of magnesium, calcium, aluminium, and iron ions. The formed precipitate is also known as soap scum. So you can see these sodium salts of fatty acids, when they are interacting with these ions that we have over here, magnesium 2 plus, calcium, ions, or Fe2 plus, Fe3 plus, and aluminium ions, these ions can interact with the soap molecules and the formed magnesium salts of carboxylic acids from calcium salts of these fatty acids, iron salts of fatty acids, and aluminium salts of fatty acids happen to be precipitates. They are not very soluble in water. So if your water contains any of these ions, when you try to wash with the use of soap, due to the formation of these precipitates, the washing action of soap will not take place. And each of these precipitates will appear white, mainly white in color. So students, this is the reason why we see the formation of soap scum, which is also another word for the precipitate that is formed here due to the hardness of water. So these are the reactions that take place when soap comes into contact with an aqueous medium that contains these ions that are listed here. Now we have hardness of water. We can briefly explain it here. In dry regions of Sri Lanka, water sourced from wells may possess a faint mineral taste. This is due to the hardness of water in the region. Now, if you have traveled to dry regions of the country, you might have noticed that sometimes when you taste water from a well or any natural water body that is purified, still you will have this mineral taste to that water. That is because there is a high concentration of, or a little bit of a higher concentration compared to the water that you source from other regions of the country. There's a bit of a different taste in these regions, or in the water that is sourced from these regions. So this is due to the presence of calcium and magnesium ions in the medium. Now, bathing in such water may result in noticeable sticky sensation and roughness in hair attributed to its elevated hardness level. Due to the hardness in water, when you are using this water to have a bath, you can see there's a bit of a sticky feeling associated with it, along with the hair would feel rough, and these are due to, again, as I mentioned earlier, the elevated hardness levels or elevated concentrations of magnesium and calcium ions. Now, defining the hardness of water. The hardness of water can be defined as the capacity of water to precipitate soap. The capacity of water to precipitate soap. This property arises from the presence of dissolved minerals such as primarily calcium and magnesium. Now, these are the main ions, and they are the ones that are most commonly causing the hardness that we see in water. When soap is introduced into hard water, these ions react with the soap molecules, forming insoluble compounds known as soap scum. Now, multivalent metals such as magnesium, calcium ions are naturally present in water, primarily accounting for its hardness. However, less commonly, ions like Mn2+, aluminium 3+, Fe3+, can also contribute to water hardness to a lesser extent. Now at this point, students, you have to understand that hardness of water is characterized by the water's ability to precipitate soap, and hardness of water is mainly caused by multivalent ions that we saw over here, like calcium, magnesium, aluminium, iron, or Fe3+ ions that we have over here. And out of these ions, calcium and magnesium are the ones that are most naturally found in water, and they are usually found in higher concentrations in water, especially in hard water. Magnesium and calcium ions are going to be found in a higher concentration. And these are the ones that are mostly causing hardness in water. Apart from that, other ions like manganese, aluminium, and Fe3 plus. Manganese, aluminium, and Fe3 plus also can cause hardness in water, but a bit more rare occurrence, because mainly the ones that cause or contributes to hardness is magnesium and calcium. These ions are not very abundant in a given water sample. Now, if you analyze this further, the hardness of water is expressed as parts per million of calcium carbonate. Parts per million of calcium carbonate. So if the calcium carbonate parts per million value happens to be between 0 and 50, we can call it soft water. Soft water. So at that point, it is not considered to be having hardness in it. And 50 to 100, we say moderately soft water. 100 to 200, slightly hard water. So you will start to notice a difference when it comes to the use of this water, when it comes to washing action, or when it comes to the taste of the water, you will notice a difference. And then moderately hard water around 200 to 300, and 300 to 450, it will be hard water. So you will very clearly observe that the soap is not lathering and the taste is very clearly different compared to soft water. And if the ppm value is 450 ppm and above, that is extremely hard water. So you have highly elevated concentrations of magnesium and calcium ions, or it could be due to the presence of other ions like manganese, Fe2 plus, Fe3 plus, and aluminium ions. Temporary hardness. Naturally, magnesium and calcium ions contribute the most towards hardness of water. However, less commonly, ions like manganese, aluminium, ferric can also contribute to water hardness to a lesser extent. When the concentration of carbonate and bicarbonate ions in water exceeds the concentration of metal ions, such as calcium and magnesium, which contribute to water hardness, the hardness in such water is termed temporary hardness. Temporary hardness. So that is very important. When the concentration of carbonate and bicarbonate ions in water. So now, students, you have to explain this part very clearly. So if you take a hard water sample, the hardness is mainly due to, let's say, calcium and magnesium ions. And in a given water sample, you can have other ions as well, like chloride ions can be present, right? You can have carbon dioxide dissolving in water and producing some carbonates, right? Carbonate and bicarbonate ions. So if the bicarbonate and carbonate ion concentration in the hard water is much greater than the calcium and magnesium in water, at that point, we say what we have is temporary hardness. What we have is temporary hardness. This type of hardness in water can be removed by boiling water. This type of hardness can be removed by boiling water. So that's something that you need to keep in mind. So you can see why we say this is temporary hardness, because at this point when you boil the water, we are going to be removing calcium and magnesium ions from water and creating soft water. So that's why we call it temporary hardness. Removal of temporary hardness of water. To remove temporary hardness, water can be boiled. You can see there are bicarbonate, so carbonate ions in the medium. And if you heat the water, or when you boil the water, due to the increased temperature, we can form magnesium carbonate and calcium carbonate, which are water insoluble precipitates. So therefore, calcium and magnesium ions in the medium can effectively be removed. Right, students? So when we heat calcium ions in the presence of bicarbonate ions in the medium, due to their interaction, you form calcium carbonate along with carbon dioxide and water. Along with carbon dioxide and water, resulting in lowering of the calcium 2 plus ions in the medium. So when calcium carbonate precipitate is formed along with these carbon dioxide and water, actually the most important part is the formation of calcium carbonate as a precipitate, because at this point calcium ions that were present in the medium is now effectively removed as a precipitate. When the same thing happens to magnesium ions that were initially present in the medium causing hardness is now removed as a precipitate. Here the magnesium and calcium ions will get precipitated as their carbonates. Then the precipitate can be removed to obtain a soft water solution. So what you have over here is soft water after boiling water. Now we move on to defining what permanent hardness is. In permanent hardened water, concentration of carbonate and bicarbonate ions is much lower than that of the metal ions responsible for water hardness. In other words, calcium and magnesium 2 plus ion concentration is higher than the carbonate or bicarbonate ion concentration in water. So that means, students, even if we heat it for long enough, the amount of precipitate that is going to be formed is not going to completely remove the calcium or magnesium ions that are present in the water. Or we have to say the precipitate that forms is not going to be able to sufficiently remove the calcium or the magnesium ions in the medium to bring down the water hardness. If the calcium and the magnesium ion concentration was lower than the bicarbonate ion concentration in water, at that point what would happen? Then we have enough and more bicarbonate or carbonate ions in water that can cause the removal of calcium and magnesium 2 plus ions as their carbonate compound. But here, in permanent hard water, the calcium or magnesium ion concentration is much higher than the carbonate or bicarbonate ion concentration in water. So therefore, just by heating it, you will not be able to remove the hardness of water effectively. Boiling water, in this case, does not effectively remove this hardness. Therefore, it is termed permanent hardness. However, to address this issue, sodium carbonate can be added externally to remove hardness. So yes, instead of now we, for example, in this case we say this is permanent hardness. However, we can still remove this hardness by externally introducing carbonate ions into the medium so that the carbonate ion concentrations are sufficiently high enough to precipitate the calcium and magnesium 2 plus ions in the medium. So at that point, when they are precipitated out completely, we have soft water formed again. So students, keep in mind, permanent hardness and temporary hardness are two different things, and the definition is important. So when it comes to temporary hardness, you have calcium and magnesium ions, but the carbonate ion or bicarbonate ion concentration in the medium is higher. But when it comes to permanent hardness, calcium and magnesium concentration is higher and the bicarbonate concentration is lower. So they are not able to completely precipitate out the calcium and magnesium ions in the medium. So if you are from an area where you have a lot of hard water, you will see if you boil this hard water, or if you are using a kettle to always boil water at home, you would observe at the bottom of this kettle you have a white color precipitate deposited on it, a hard white color precipitate deposited on it. So that is due to the heat that you provided. Some amount of calcium and magnesium ions got removed from the water as their carbonate and it got precipitated in the kettle. So students, that is why you observe the white color precipitate at the bottom of your kettles. So this will reduce the hardness of water a little bit as well. So if it was permanent hard water, it will not completely remove hardness. If you want to completely remove hardness from permanent hard water, you have to externally add the carbonate ions through addition of sodium carbonate. Sodium carbonate dissolves in water and releases carbonate ions into the medium. And at that point, the carbonate ion concentration will be sufficiently high enough to be heated and remove the calcium and magnesium ions from the medium as their carbonate. So you can see here, when you add these, you can see the formation of calcium and magnesium carbonate in these reactions. So at this point, we will bring down the calcium and magnesium ion concentration sufficiently to call it soft water. When sodium carbonate is added to the precipitation, due to the precipitation of magnesium and calcium ions, water will be soft again. Washing action of soap. I briefly explained this to you a little while ago, so we have now a small diagram to explain it to you. Dirt is a mixture of dust particles and organic substances. Due to the high surface tension of water, dirt is washed with just water. When dirt is washed with just water, it will not be washed away. Soap reduces the surface tension of water and enhances the washing process. Now, polar substances dissolve in water. Oil and grease are not polar and do not dissolve in water. So now, students, actually, when it comes to soap, this is also having two main parts. It has a hydrophilic head and hydrophobic tail. And as I mentioned earlier, if the substrate is coated with some sort of a oily or greasy substance, just washing it with water might not effectively remove all of the dirt. However, when you are washing it with water, the hydrophilic section of water will not dissolve in the greasy material or the dirt, but the hydrophobic tail part, as indicated over here, will dissolve in the oil droplet or the grease or the dirt particle, and it will expose the hydrophilic heads of the soap molecule to the exterior. So the exterior now appears as if it is coated with the hydrophilic heads of the soap molecule. So this can easily interact with water because hydrophilic heads dissolve in water and dissolve the entire dirt particle along with it in water. And what you form over here when the hydrophilic tails are dissolved in the oil or the grease particle is referred to as a micelle. So due to micelle formation, the dirt particles or oil or grease can be washed with the use of soap. The nonpolar nature of hydrophobic tail in soap molecules allows it to dissolve in dirt particles. Conversely, since hydrophilic head is not soluble in oil, it remains exposed to the exterior of the dirt particle. So, if you have the dirt particle over here, the entire exterior of the dirt particle is now going to consist of mainly hydrophilic heads. So I will not draw individual heads here. You can see if the red color circle indicates our oil droplet, the entire exterior of the oil droplet is now covered with hydrophilic heads of our soap molecules. Now, from the exterior, this looks like something that dissolves in water. Why? Because you have water which is polar and the oil droplet is now covered with something that is polar. So therefore, it dissolves in water. It remains exposed to the exterior of the dirt particle. Consequently, the entire outer surface of oily dirt particle become coated with hydrophilic heads of soap molecules, a phenomenon that is known as micelle formation. So whenever an entire oil droplet is covered with exposing the heads of the water, exposing the head of heads of soap molecules to the exterior of soap molecule. What you form over here is known as micelle. So this process is known as micelle formation. So the washing action of soap, again we continue the same topic here. So you can see in water the hydrophilic heads dissolve, in oil the non-polar section of soap molecule, which is the hydrophobic tail, dissolve, right? So oil is non-polar, hydrophobic tail is non-polar, they dissolve in one another. Water is polar, hydrophilic head is polar, they dissolve in one another. Actually, when it comes to soap, we can also call it a surfactant, right? So it allows these two immiscible layers to mix due to the molecule itself having one section that is dissolving in polar layer and another section that is dissolving in non-polar layer, right? Important details about soap. It is made using biomass, plant oils or animal fats can be used to make soap, right? So we know very well it is not made through any other artificial product. We use plant oils or animal fats. When introduced to the environment, it can undergo biodegradation. Yes, so basically what we have over here is fatty acid sodium salts, and as we know, plant products can undergo biodegradation. So this can very well undergo biodegradation. So the release of soap into the environment is not going to cause an accumulation of soap in the environment because it is biodegradable. Cannot be used in acidic medium. You can't use soap in acidic medium. It cannot be used in hard water as well. Soap not lathering in hard water is a drawback associated with soap. However, detergents do not show this quality. So there are some drawbacks to soap. Some, right? You can't use it in acidic medium. You can't use it in hard water. So therefore, to address these issues, we actually have another substance that is known as detergents. Now, if you talk about detergents, this is also a washing agent. This can be manufactured in liquid or solid form. You might have seen these types of detergents in different shops. You will have used them in your washing processes as well. So these can be manufactured as a liquid or solid, right? We have liquid detergents or solid detergents. In the washing process, oil and dirt can be removed. Do not get affected by the hardness of water. The hardness of water does not affect the washing process. The hardness of water does not affect the washing process, so there's no problem there. The main chemical found in manufactured detergents is sodium alkyl benzene sulfonate, is basically sodium alkyl benzene sulfonate. So the structure of sodium alkyl benzene sulfonate is given over here, and that is a detergent molecule. Now earlier we saw when it comes to soaps, they are not very effective in acidic medium. As you know, when soap is dissolved in water, you form the carboxylate anion and sodium ion because the soap molecule will ionize in water to form carboxylate ion and the sodium ion. And in the presence of higher concentrations of H plus or lower pH or high concentration of H plus and the carboxylate anion can get together and form carboxylic acid again. Now carboxylic acid will not show the washing action that we saw earlier, because in order for the washing action to take place, we have to have the hydrophilic head and the hydrophobic tail, meaning the carboxylic acid should exist in its deprotonated state as the carboxylate anion. So when H plus concentration in the medium is high, the H plus and the carboxylic anion will react together to form the carboxylic acid again. So therefore, students, it will not carry out the washing action. So students, that is another piece of information that you have to have with you. And then let's take a look at the detergent. So basically, we have this detergent that is used in many washing processes. We can obtain it as a liquid or a solid, as I mentioned earlier. And the main component that is found in these detergents is sodium alkyl benzene sulfonate. Sodium alkyl benzene sulfonate, and the structure of it is given over here. Right. So let's move on to the next part. As seen in soap, detergent molecules also possess a hydrophilic head and a hydrophobic tail. However, having a structure that is different from soap gives rise to different properties in detergents. So, although this also has a hydrophilic head and hydrophobic tail, the structure is different. So, therefore, students, how they behave is different to one another. So, different types of detergents are there. We have anionic detergents, cationic detergents, and non-ionic detergents. So, we will take a look at them individually here. Now, anionic detergents have negatively charged hydrophilic head and are effective at removing oil and grease. So, hydrophilic head part is negatively charged. Negatively charged hydrophilic head is there. So, when you talk about the main section of this detergent molecule, this is our negatively charged hydrophilic head. Now, along with it, we can see a sodium ion attached to it. However, this section is the negatively charged hydrophilic head. So, we call it an anionic detergent due to the hydrophilic head section being negatively charged. And of course, hydrophobic tail section is consisting of carbons and hydrogens. And then we have cationic detergents. These detergents have positively charged hydrophilic heads. You can see the head section, hydrophilic head section is positively charged. Right? So, these are referred to as a cationic detergent, and the hydrophobic tail section is again made of only carbons and hydrogen. It is not polar. And these are effective at disinfecting and sanitizing surfaces. They are often used in fabric softeners, hair conditioners, and certain types of household cleaners. So, they are mainly good for these purposes that are mentioned over here. And earlier we mentioned these are very good for removing oil and dirt. Anionic detergents, cationic detergents are specifically good for sanitizing surfaces, fabric softeners and hair conditioners, and some other types of household cleaners. Non-ionic detergents. As the name suggests, students, in this particular detergent, especially in the hydrophilic head section, you don't have ions present. So, you can see over here in the text, these detergents have a neutral or uncharged hydrophilic head. The hydrophilic head part is basically neutral or uncharged, but it is polar, but it is not carrying a charge. And are gentle on fabrics and skin. So, these detergents are said to be gentle on fabrics and skin. They are not necessarily harsh detergents. They are suitable for washing delicate fabrics such as silk or wool, and are commonly found in baby detergents, facial cleansers, and shampoo formulations. So, students, these type of detergents, since they are somewhat gentle on the skin and gentle on fabrics, we find these in the above products. And you can see there are no ions here. This entire section is polar, right? And the rest of the molecule is going to be non-polar. So, that is our hydrophobic tail, and this polar section without any ions is referred to as our hydrophilic head. So, you can see hydrophilic head section can have interactions with water molecules. And not just any interactions, They are capable of forming hydrogen bonds. So they dissolve, that section dissolves well in water. Now, uses of detergents. Now, detergents will not precipitate in hard water. That is a very important use. We saw when it comes to soap, in hard water it precipitated. So therefore, we will not be able to carry out any washing action with the use of a normal general soap when we have hard water. But detergents, we don't have such a problem. They can even carry out their washing action in hard water. They can even in hard water they can carry out their washing action. Therefore, it is more popular among consumers for washing purposes. However, they do not undergo biodegradation. Therefore, it can cause environmental pollution, unlike soap. So that is a problem, students. Now, this is more popular. If you walk into any store that sells soap and detergent, you will see for washing purposes, like general washing purposes, detergents are more popular. When it comes to washing clothes, you will see that on a regular basis, majority of the consumers prefer detergents to the use of soap. So, however, this is causing an environmental problem because detergents do not undergo biodegradation. So, this can cause environmental pollution. To reduce environmental pollution caused by detergents, the focus has been directed to producing detergents that can undergo biodegradation. So that is a main area that research is focusing on, because since there is a preference for the use of detergents over the use of soap for certain washing processes, we are now focusing on producing detergents that can undergo biodegradation, so therefore will reduce the environmental pollution caused through detergents. Preparation of soap in the lab. So preparation of soap in the lab is not too complicated, students, and when it comes to this process, you'll be needing a few equipment. So let's first go through them. We'll be needing Bunsen burners, Buchner funnel. Now, Buchner funnel is quite important when it comes to separating the soap from the reaction mixture. We'll be needing beakers and magnetic stirrer. And apart from that, we need chemicals such as coconut oil, sodium hydroxide, and sodium chloride. Now, this outlines a procedure for producing soap. So we use around 250 cubic centimeters of centimeter conical flask and add 25 cubic centimeters of vegetable oil or coconut oil. Either one can be used. And 20 cubic centimeters of ethanol and 25 cubic centimeters of 6 moles per decimeters cube concentrated sodium hydroxide into the flask. So you can see the sodium hydroxide concentration is somewhat high because we need sodium hydroxide for this hydrolysis process. Then we heat the mixture. Actually, we start stirring the mixture really well, and then we heat the mixture using a boiling water bath and stir continuously to prevent the formation of foam shown in the figure, and heat the mixture for a period of 5 to 10 minutes, and the mixture will transform to a paste at the end of heating. So we are heating the mixture while stirring the mixture. So we will place the mixture. Now, if you have a hot plate with a magnetic stirrer in it, you can actually place your mixture on the hot plate and maintain temperature there along with continuous stirring. If you don't have such a setup, you can actually place your reaction mixture in a water bath and maintain the temperature around 70 degrees Celsius. And as the reaction takes place, you need to keep stirring the reaction mixture. And after a while, you will see the formation of a paste-like substance. So after the heating, remove the mixture, now soap, from boiling water and boiling water bath and cool down using an ice bath. So when you cool it down using an ice bath, you can see that precipitate form of soap is going to be produced more and more. Earlier on, the paste might not be very thick, but when you cool down the reaction mixture, the paste will become a bit more thicker and very clearly forming soap as a precipitate. Add 150 cubic centimeters of saturated sodium chloride to cool soap mixture and filter the soap using Buchner funnel with a weighted filter paper. A sketch of the filter paper setup is given in the images below. So I'll show you the image in a second. So students, sometimes when you carry out this reaction at higher temperature, initially the prepared soap might not very well be clear to you and it will not be very observable as a paste. You might feel that the medium is somewhat thicker now, but the formation of soap, white color precipitate, is not going to be somewhat very clear to you. Even upon cooling, you will only see a little bit of soap, but not a lot. But when you add sodium chloride or brine solution into the medium, you will immediately see a lot of soap getting formed and precipitating out as a white color precipitate. So this is your soap. And then we can actually move on to filtering out the soap that is produced. Now soap along with this glycerol that is present here, it's going to be somewhat sticky and slimy in nature. When you prepare this in the lab, you will observe this. So at that point, students, gravity filtration can be done to remove water, but it will take a long time. So to save us time and carry out a more effective or efficient filtering, we can use a vacuum filtering setup. So when we use a vacuum filtering setup, we need the Buchner funnel. So Buchner funnel is prepared by adding a filter paper that snugly fits on the Buchner funnel, and then we are going to transfer our reaction mixture, or now in this case it's a product mixture. You transfer the mixture to the Buchner funnel, and we will allow the vacuum to more efficiently filter the aqueous layer along with any other liquid layers that are in the solid soap. So once you carry out this filtration, you will obtain solid soap. Now in the lab setup, when you do it, the soap that is produced is not going to be entirely dried with the use of the vacuum filtration. It will still be somewhat wet, but you will be able to observe the properties of soap, like the washing action, or if you take a little bit of soap and dissolve it in water, you can see the formation of bubbles. So when you are using the Buchner funnel, make sure to position the filter paper so that it fits snugly at the bottom of the Buchner funnel, ensuring that no edges of the filter paper extend up the walls of the funnel. Now if this happens, some amount of soap can go passing the filter paper without going through the filter paper. So then some soap particles can get added into the solution that is coming over here into the flask. Now after filtering out all of the solid soap, you can put it in a mold and prepare a soap bar, right? So we also refer to this as a soap cake or soap bar. So this can be molded. First of all, when you get the precipitate over here, it does not necessarily have a shape. It's just basically a soap precipitate that you get. So you can get it and collect it and put it into a mold and press it to produce a bar of soap like this. So students, this process can be done in the lab with the use of the chemicals and the equipment that I mentioned earlier. And when you're using or when you're carrying out this experiment, make sure to use the right temperatures and make sure to understand what kind of processes are taking place in each step. So, with that, we can conclude the theory parts revolving around the manufacturing of soap. So, in theory parts, we looked at what are the main raw materials we'll be using for this, and within the raw materials, what are the main components that are going to be used or that are actually getting converted into soap. We looked at triglycerides and the hydrolysis process of triglycerides, which lead to the production of soap. So this process of alkaline hydrolysis of triglycerides were referred to as saponification, and through the saponification you form two main products, soap and glycerol. We learned about how to precipitate soap out as well as how to remove glycerol. So these are the main parts that we looked at in the theory discussion of this experiment. So now students, it is time for us to move on into the lab and conduct this experiment. So let's move on to the lab.
GCE Advanced Level Chemistry Experiment Series, experiment number 41. Preparation of a soap sample in the laboratory. In this experiment, we aim to provide you with the necessary knowledge and the skills required to prepare a small sample of soap under laboratory conditions. Now, let's move on to identifying the reagents and the equipment we will be using to conduct this experiment. Let's take a look at the chemicals and the equipment we will be using for this experiment. For this experiment, we will be using sodium hydroxide, also referred to as caustic soda. We will be using ethyl alcohol or ethanol. We have sodium chloride here, coconut oil, distilled water, measuring cylinders, conical flasks, beakers. We will be using a thermometer as well to measure the temperature, stirring rods or glass rods for stirring. We will be using filter papers, a watch glass, a spatula, and a digital balance that we have here to measure the amount of sodium hydroxide we need to produce 6 moles per decimeters cube sodium hydroxide solution. We'll be using a digital balance, watch glass, and a spatula. Apart from that, we will be using a Buchner funnel, a water bath. So you can see a water bath set up here. We have a beaker here filled with water and placed on a tripod, and we'll be using a Bunsen burner to complete the setup of a water bath. Apart from that, we'll be using a retort stand with a clamp as well. So these are the equipment and the reagents we will be needing for this experiment. Now let's move on to conducting this practical. Now, in the first part of our practical, we will be preparing a sodium hydroxide solution that has a concentration of 6 moles per decimeters cube. We will be needing this solution when preparing our soap sample. So let's move ahead and prepare a solution of sodium hydroxide that has a concentration of 6 moles per decimeters cube. In this experiment, we will be using 25 cubic centimeters of 6 moles per decimeters cube sodium hydroxide. So here we are going to be preparing 50 cubic centimeters of sodium hydroxide in case we need to do it twice. We will be using a measuring cylinder to measure the amount of water we will be adding to the sodium hydroxide. And with the use of digital balance here, we are going to be measuring the amount of sodium hydroxide that we will be needing to prepare this solution. To prepare a 6 moles per decimeters cube solution with a volume of 50 cubic centimeters, we would need 12 grams of sodium hydroxide. Students, we will not be using a volumetric flask to prepare this solution, as we are not planning on doing a titration with it, so we do not necessarily need to be very precise with the solution that we form. We need to have a sodium hydroxide concentration of roughly 6 moles per decimeters cube. So we will be using a beaker to mix the sodium hydroxide and water, and measuring the amount of sodium hydroxide we need is going to be done with the use of a digital balance, and the water we need is going to be measured with the use of a measuring cylinder. Now, let's take our digital balance. Let's turn it on. You can see the digital balance reads 0. We can place our watch glass, and to remove the mass of the watch glass from our reading, we can tear the digital balance. So now the digital balance reads 0. After that, we will take our sodium hydroxide pellet sample that we have over here. In this bottle, we have sodium hydroxide pellets. We need to measure 12 grams of sodium hydroxide. So let's take 12 grams of sodium hydroxide onto our watch glass. Students, we have measured 12.08 grams of sodium hydroxide. Now, we are going to transfer it into a beaker and then add 50 milliliters of distilled water. So we have a beaker here. Let's transfer this 12.08 grams of sodium hydroxide, and to that we can add 50 milliliters. We can add 50 milliliters of distilled water. To measure 50 milliliters of distilled water, we can use a measuring cylinder that we have here. Students, we have measured 50 cubic centimeters of water now. Now, let's add our water to our sodium hydroxide. Dissolving sodium hydroxide in water is going to be an exothermic reaction, so you will feel the solution heating up. So we are going to dissolve this sodium hydroxide in the water completely, and we will allow it to cool down to room temperature before moving on to the next part of our experiment. Now students, we have prepared our 6 moles per decimeters cube sodium hydroxide solution here, and we have allowed it to cool down to room temperature. So in this beaker, what we have here is 6 moles per decimeters cube sodium hydroxide at room temperature. The reason why we mention that it is at room temperature is because dissolving sodium hydroxide in water is an exothermic reaction. When you conduct this experiment, you would notice the temperature of the solution increases drastically when you are trying to dissolve this sodium hydroxide in water. So at that point, the temperature will be quite high. So we have to make sure that you allow it to cool down before we continue on with the rest of the reaction. And To conduct the rest of the experiment, we will be using a conical flask. To this flask, we need to add 25 cubic centimeters of coconut oil and 20 cubic centimeters of ethanol, and to that mixture we are going to add our sodium hydroxide solution. Students, in the industrial manufacturing process of sodium hydroxide, it usually consists of about 4 different steps. The first step is referred to as the saponification step, where sodium hydroxide is reacted with the coconut oil to carry out a hydrolysis reaction. Now students, coconut oil or plant oils contains triglycerides. These triglycerides are made with glycerol molecules reacting with long chain fatty acids to form ester bonds between them. When you react an ester with sodium hydroxide, and if you provide the reaction mixture some heat, an ester with sodium hydroxide, the ester bond will break and an alcohol and the sodium salt of a carboxylic acid will be formed. In this case also, when we use a triglyceride and heat it in the presence of sodium hydroxide, the ester bonds in the triglyceride will break and will form glycerol. As usual esters form alcohols, when it comes to a triglyceride, what you see as one of the products is glycerol. Apart from that, you'll be forming sodium salts of carboxylic acids. So when it comes to an ester, you form alcohol and sodium salts of carboxylic acids. When it comes to triglycerides, you're going to be forming glycerol and sodium salts of carboxylic acids. So the sodium salt of carboxylic acid that is formed is what is referred to as soap. So RCOONA is the general formula of the soap that is formed. We can call it the sodium salt of carboxylic acids. And these carboxylic acids are not short chain carboxylic acids that you observe usually in the lab. When it comes to triglycerides, you are going to observe long chain carboxylic acids. When it comes to coconut oil, you are going to have lauric acid, which has about 12 carbon atoms in it. Lauric acid has 12 carbon atoms in it. We have myristic acid, which has 14 carbon atoms in it. We have palmitic acid, which has 16 carbon atoms in it. And we have stearic and oleic acids, which normally contain 18 carbon atoms in it. So you can see these are long chain carboxylic acids. We call them fatty acids or long chain fatty acids. So when you add the coconut oil and react it with sodium hydroxide, you are going to form carboxylic acid salts or sodium salts of these carboxylic acids. Apart from the triglycerides in coconut oil, there will be a small portion of free fatty acids in the oil as well. So these free fatty acids will also react with sodium hydroxide. As you know, if you take a carboxylic acid and react it with sodium hydroxide, you will form, one of the products that you form is sodium salts of the carboxylic acid apart from the water that is formed. So this is a neutralization. If you take the free fatty acid and react sodium hydroxide with it, you are going to form sodium salts of the carboxylic acid. So all of these components in the coconut oil, the triglyceride and the free fatty acids that are found in the coconut oil, will react with sodium hydroxide to produce RCOONA, which is a general formula for the soap that is getting formed here. So sodium salts of the carboxylic acids that are formed in this reaction is referred to as soap. And this reaction where we react coconut oil with sodium hydroxide is referred to as a saponification reaction. We call this reaction a saponification reaction. Now, without any further delay, let's take 25 cubic centimeters of coconut oil into this conical flask. We have a measuring cylinder here, and we have our coconut oil. Let's take 25 cubic centimeters of coconut oil. We have measured 25 cubic centimeters of coconut oil, and to that we are going to add ethanol. We are going to measure 20 cubic centimeters of ethanol. So we have our ethanol here. We will be adding 20 cubic centimeters of ethanol onto our coconut oil we have here. So students, we can very clearly see we have measured 20 cubic centimeters of ethanol as well. Now students, why do we add ethanol into the mixture? We need only the coconut oil and sodium hydroxide. What is the purpose of adding ethanol? Coconut oil and sodium hydroxide, which is an aqueous solution, do not mix really well. Coconut oil does not mix well with water. So the reaction will only happen at the interface of these two aqueous and oil layer. So because of that, when it comes to the reaction, it will be difficult for the reaction to take place if these two layers don't mix really well. So to facilitate mixing of the two layers, we can add ethanol, as ethanol is capable of dissolving certain amount of the oil that we have here, as well as ethanol is capable of dissolving in water as well. So we can say that ethanol can act as a co-solvent to make sure that this reaction takes place in a more efficient manner. So that is the reason why we add ethanol. Ethanol acts as a co-solvent. It is soluble in oil as well as in water. So now we can transfer our 25 cubic centimeters of coconut oil into our conical flask. Since coconut oil has a bit of a higher viscosity, it will take some time for all of the coconut oil to get transferred into our conical flask. After transferring all of the coconut oil, we can now transfer our 20 milliliters of ethanol. Now students, you can see they do not necessarily form very distinctive two layers. Ethanol and our oil slightly mix with one another to form a single layer. If it was just water that is added to the coconut oil layer that we have here, you will very clearly see two layers formed here. But here, some of the coconut oil that we have dissolves in the ethanol that we added to this reaction mixture. Students, before we move on to adding sodium hydroxide to our reaction mixture, we can light our Bunsen burner and prepare our water bath to receive the reaction mixture. So this reaction should be carried out at around 70 degrees Celsius. So we will wait till the water bath reaches this temperature, and then we will mix our sodium hydroxide with the coconut oil and ethanol mixture, and then we will place our reaction mixture in the water bath. So let's turn on our Bunsen burner. Now students, we have our water bath set up here, and the temperature of the water bath is at around 70 or little over 70 degrees Celsius. So now we can introduce our reaction mixture into this water bath. We have in front of us our conical flask that contain 25 cubic centimeters of coconut oil and 20 cubic centimeters of ethanol. So to this, we are going to add 25 cubic centimeters of sodium hydroxide, and the concentration of the sodium hydroxide solution is 6 moles per decimeters cube. We will take a measuring cylinder and measure 25 cubic centimeters of sodium hydroxide. We have measured exactly 25 cubic centimeters of sodium hydroxide, and now all that is left for us to do is add this 25 cubic centimeters of sodium hydroxide to our reaction mixture here, and then we are going to continuously stir it while heating the reaction mixture and maintaining the temperature of the reaction mixture around 70 degrees Celsius. So let's add these two together. This is a neutralization reaction that is taking place. So you will observe the reaction mixture heating up a little bit. There are free fatty acids reacting with sodium hydroxide, so there is a neutralization reaction taking place here. Now we will fix our conical flask on this clamp like so, and then we will lower this onto our water bath. And we will continuously stir this reaction mixture so that the reactants can come into contact with one another really well. As you know, the sodium hydroxide layer and our coconut oil is not very miscible in one another. To facilitate the mixing of the two layers, we added a small amount of ethanol as well as a co-solvent, but nonetheless, you will have to keep mixing this reaction mixture for the reaction to take place more efficiently. Students, you have to continuously stir this mixture because if you do not stir it, there will be formation of foam, and to prevent accumulation of foam, you will have to continuously stir this mixture. Like I mentioned earlier, we have the aqueous layer and the oil layer. They are not very miscible, and the reaction will only take place where the two layers meet, which is the oil aqueous layer interface. So in this interface, the reaction will take place and will produce sodium salts of different carboxylic acids. So that is referred to as soap. So to make sure that this reaction happens efficiently and comes into contact with the reactants efficiently, you have to continuously stir this reaction mixture while keeping this reaction mixture at a temperature of around 70 degrees Celsius. Now we will continuously stir it for about 10 to 15 minutes. Towards the end of this time, you will observe the formation of soap. Now students, we are here to observe what takes place after about 5 minutes of stirring. You can observe that the two layers are now no longer visible as two separate layers, although both of those layers are still present in this mixture. Since we are continuously stirring this mixture, you can see it appears to be one single layer. And apart from that, the solution has turned a bit more cloudy than it used to be. This is because of the formation of soap. So now we'll continue to stir this reaction mixture until a paste is formed at the bottom of this reaction mixture. At that point, we can be certain soap has been produced, and we can separate the soap out and move on to our next step. Now students, after stirring this reaction mixture for a while, you are going to come to this observation. Initially, when we mixed the oil and the sodium hydroxide aqueous solution, you saw the formation of two layers. But now, after we have completed our reaction, one of the observations you are going to have is that you do not observe two layers present here. You can see there's only one layer found in this reaction mixture. This is also an indication that all of the oil that we introduced into this reaction mixture has reacted with the excess of sodium hydroxide that we added to this reaction mixture. So now we can call this solution a soap solution because we have formed soap here. Now students, in this reaction mixture, the main product that you find is soap. The triglycerides have reacted with sodium hydroxide. The free fatty acids that are present in the oil has reacted with the sodium hydroxide to produce sodium salts of carboxylic acids. So what you have here is sodium salts of carboxylic acid and glycerine. Since the main product that you find here is sodium salts of carboxylic acids, we can call this soap mixture here from here on out. We can now call this our soap mixture. Now, all that is left for us to do is cool the mixture and observe soap being formed as we cool this mixture. So let's move on to placing this mixture in an ice bath. Now students, we have our ice bath here, and we are going to place our reaction mixture, now referred to as soap mixture, in this water bath. So we are going to allow this soap mixture to cool down to room temperature, and then afterwards we will move on to the next step where we will be adding a brine solution and separating the soap that is present in this aqueous solution, because right now some of the soap that we have here is dissolved in water. There's a little bit of glycerol also that is dissolved in water, but when we add salt or brine solution into this, we are able to separate the soap from our aqueous solution. So students, we will let this solution cool down first, and then we will move on to the addition of our brine solution. You can see even as it cools down, there is no layer separation that is found here. This is one aqueous layer now. In this aqueous layer, we have our soap and we have our glycerine or glycerol. Apart from that, there will be some excess sodium hydroxide that we used dissolved in this aqueous layer. So we will allow it to cool down now, and we will come back again after it has completely cooled down to room temperature. Now students, we have allowed the soap that we produced to cool down in the ice bath. I will take it out. You can observe the clumpy nature of the soap that is formed here. So we have produced soap here. It has clumped up mainly due to the presence of glycerine also in the mixture. So if you remove this ice bath from here, we can talk about what is found in this mixture that we have here. So in this aqueous layer that we have here, we mainly find uh, sodium salts of carboxylic acids, or the general formula of that would be RCOONA, which is the soap that we are referring to. So soap has the general formula RCOONA in this case. So sodium salts of the carboxylic acids that is present here is referred to as soap. Apart from that, in the aqueous layer, you find glycerine dissolved, or glycerol. Right, small portion of glycerol will be found in soap as well. Apart from glycerol, there is a certain amount of sodium hydroxide, because when we were reacting the coconut oil with sodium hydroxide, we used excess sodium hydroxide. So there is definitely a small amount of sodium hydroxide present in this aqueous layer. So now, in this aqueous layer, the soap that we referred to, the RCOONA that we referred to as soap, is present in the ionized form. Sodium salts of carboxylic acids can get ionized to form the carboxylate anion and the sodium ion. So these are present as two separate ions in the aqueous medium, and there is an equilibrium between the ionized form of soap and the non-ionized form of soap. So if you add concentrated sodium chloride solution, we have concentrated sodium chloride solution, actually a saturated solution of sodium chloride. We prepared this by dissolving an excess amount of sodium chloride in a small amount of water, or 100 milliliters of water. So you can see a small portion of sodium chloride is still not dissolved in this medium, because this medium is saturated with sodium chloride. So in this sodium chloride solution, or the brine solution, we have a high concentration of sodium 1 plus ions. So when you transfer sodium ions into this, or when you transfer a small amount of this brine solution or concentrated sodium chloride solution into our soap, what happens is the equilibrium that we spoke of earlier, in that particular equilibrium, the equilibrium position shifts more towards the left-hand side, producing solid soap, or non-ionized form of soap. As you remember, in aqueous medium, the RCOONA is ionized into sodium ions and the carboxylate anion. If the sodium ion concentration goes up, the reaction shifts to the left, producing more and more solid RCOONA. So at this point, you can actually observe the formation of solid soap in the mixture that we have in front of us. So students, solid soap has the general formula RCOONA, or solid soap is basically the sodium salts of carboxylic acids. Now, if you take solid soap, or RCOONA, and add water to it, the solid soap will dissolve in water and will get ionized to produce the carboxylate anion and sodium plus aqueous ion. So the carboxylate anion and the sodium plus aqueous ion will be in the aqueous medium. So between the solid soap and the ionized soap, there is an equilibrium. if you increase the sodium ion concentration in the medium, due to a high sodium ion concentration in the medium, the equilibrium position will be shifted to the side where there is more and more solid soap or solid RCOONA, which is not ionized. So in this step of our experiment, what we are going to be doing is we are going to add a concentrated brine solution into our soap that we have here, which is ionized. In the aqueous medium, the soap that we have here is mainly ionized. Majority of the soap that we have here is ionized. So when you add sodium chloride or high concentration sodium chloride, it will bring a high concentration of sodium plus ions into the aqueous medium, causing the solid soap to precipitate out. So to observe this better, we can do this in a beaker, because when we form the soap, it will be easier for us to transfer this soap into another container when it is done in a beaker. Now students, we have taken the soap into a beaker, and to this we are going to add our brine solution that we have here. So as we add the brine solution, you are going to notice the soap that is ionized in this aqueous medium is starting to precipitate out as a solid. So let's observe that now. Now students, as I added brine solution into the soap that we had here, we could see the ionized form of soap started precipitating out as a solid. So the carboxylate anions of these carboxylic acids that we had earlier is now present here as carboxylate anions. When they encountered a really high concentration of sodium, they got precipitated out as sodium salts of carboxylic acids or sodium carboxylate salts. So what we have here is soap or solid soap that is produced upon the addition of brine solution. I have not mixed it yet, but you have to make sure to mix it thoroughly while adding a little bit more sodium chloride solution. So let's mix it thoroughly. Let's add a bit more brine solution. We'll keep adding more brine solution to make sure we precipitate out majority of the ionized soap in our aqueous medium. Students, when we started off, we had the ionized soap solution over here, which was an aqueous layer, and to that we added our concentrated sodium chloride or saturated sodium chloride solution. And as we added the sodium chloride to our soap solution we had here, we saw soap started to precipitate out as a white color precipitate. As the concentration of sodium plus ions increased in the medium, soap started precipitating out as a white color solid here. And now we have quite a bit of soap formed here. Apart from the soap, we have over here glycerol and certain amount of sodium hydroxide as well. So now it is time for us to separate this solid soap that is formed here with the use of a Buchner funnel. And since we can't use a vacuum pump inside our facility here, we will be filtering this soap with the use of a Buchner funnel through gravity filtration. We will not be using a vacuum pump. However, we will observe the soap will get separated from the aqueous medium that we have here. Students, you have to keep in mind when you're trying to filter this soap that we have formed here, you always can use more brine water to wash it further. But keep in mind, do not use just water, because in the presence of normal water, the soap will dissolve and you will lose some of the soap that you have formed. If you have to wash it further, please use brine water, or you can use concentrated or saturated sodium chloride solution. Now, let's move on to filtering this soap and separating the glycerine and hydroxide layer that is found in this soap. Students, we have our Buchner funnel, and we will not be connecting this Buchner funnel into a vacuum pump. Instead, we will be carrying out gravity filtration, but still with the help of a Buchner funnel, because it will be easier for us to collect the soap that is remaining on the Buchner funnel when we use this type of funnel. So we will be placing our Buchner funnel on a holder like so, and then we can place a conical flask to collect the filtrate. And we have here our soap and aqueous layer mixture. And before we add the soap and the aqueous layer onto the Buchner funnel, we will be using a filter paper to cover the holes that are found on the Buchner funnel. As you may know, the Buchner funnel usually contains holes like so. So you have to place a filter paper in such a way to cover the holes. And afterwards, you can add a few drops of water to fix the filter paper in place. Now students, the filter paper should not be climbing up the walls. It should only be covering the holes that are found on the Buchner funnel. It should not be climbing up the walls. So that is something to keep in mind when you are setting up your Buchner funnel. Now, since we have fixed our setup here, we can now start pouring our soap mixture into our Buchner funnel here. And we will allow the soap mixture here to get filtered and remove all of our aqueous brine solution and glycerine that is found on the aqueous solution to our conical flask here. So we will be separating out the solid soap from the aqueous layer that is found in this mixture. Now students, it has been a while. We were able to filter out the solid soap in one portion of our soap sample, and now let's transfer the other portion. We have another small portion here. We'll transfer that portion of our soap into the Buchner funnel that we have here. Now we have transferred the remainder of our soap also into our Buchner funnel, and the aqueous medium will get filtered out and will get collected into this conical flask. So the aqueous medium should contain a portion of the glycerine that was formed through this reaction, through the saponification reaction. We saw we formed glycerine. So in this conical flask, there will be a portion of glycerine that separates out. Apart from that, some amount of the sodium hydroxide that was present in the aqueous medium will also be present here. Keep in mind, students, after filtering out the aqueous layer with the use of a Buchner funnel, we will have majority of our aqueous layer separated out into a conical flask. But a small portion of water and sodium hydroxide and glycerine will still remain in this solid soap that we will have remaining in our Buchner funnel. So it is not just solid soap that is going to be found on our Buchner funnel. It will contain the soap that we have here after the filtering is complete, will contain portions of water, small portions of water. We will have a small amount of glycerine, and apart from that, sodium hydroxide will also be present here. Although in this practical, we will not explore how we can purify the soap further. Industrially, when you're manufacturing soap, having some of these byproducts, such as sodium hydroxide in soap, is harmful to the user. It could cause irritation to the skin. Apart from that, sensitive tissue like eyes can get damaged due to the presence of sodium hydroxide in soap. So therefore, we have to purify the soap a bit further. We will not be doing that in this experiment. However, for your knowledge, as this soap gets filtered out, I can explain to you how these products can be removed from our solid soap. So when it comes to water, we need water only about 12% by mass of soap. So we are going to heat the soap up to 120 degrees Celsius, and we are going to pressurize this soap and release this soap into a low pressure area as droplets. And when soap is sprayed into a low pressure area as droplets, majority of the water will evaporate, and we will continuously do this until the soap that is produced has around 12% of water by mass. And at the end of this process, you are going to obtain soap in the solid form. Before removing water, we can move on and remove some of the glycerine that is found in water. So glycerine can be removed by adding more and more brine solution into our soap and mixing these two together really well. So as you may know, glycerine is soluble in water. So as you add more and more brine solution, it is going to dissolve in the brine solution. Although brine solution contains high concentration of sodium chloride, it is not going to affect the solubility of glycerine. So glycerine will get dissolved in the brine solution, and we can separate out the soap by filtering the brine solution away. But we keep a small percentage of glycerine in soap to give it a little bit of additional smoothness and softness. So we do not remove all of the glycerine that is attached to soap. Only a portion of the glycerine will be removed from soap. Apart from that, soap might contain sodium hydroxide. Like I mentioned, it is harmful to the user. So we can remove the sodium hydroxide by reacting the excess sodium hydroxide found in soap with acid like acetic acid, or we can even use a fatty acid that is usually found in the oil that we use. For example, when you use coconut oil, you have lauric, myristic, and palmitic acids. So we can add just a small portion of lauric acid to react with the excess sodium hydroxide found in soap. So as you may know, the sodium hydroxide will react with these fatty acids. Although we call them fatty acids, these are still carboxylic acids. So carboxylic acids show a reaction with sodium hydroxide and will produce more soap, because you are going to produce sodium salts of carboxylic acids or sodium carboxylate salts, which are basically referred to as soap. So to remove the sodium hydroxide in soap, what you can do is react the remaining sodium hydroxide with an acid like citric acid, or you can add acid that is usually found in oils as well, such as lauric, palmitic, or myristic acids. So this is how you would remove the impurities found in soap. After the impurities are removed, you can add fillers, different types of fragrances and colors to produce a final product. This is referred to as finishing process of soap. And students, keep in mind, in a cake of soap or in a finished soap bar, or we call it a cake of soap, you're going to find 54 to 56% of actual soap. The rest of the percentage is going to contain water, glycerin, different types of fragrances, colors, and different types of fillers. So this soap content is usually communicated with the term total fatty matter, or we will call it TFM. So total fatty matter refers to the amount of sodium source of the carboxylic acid that is found in soap. In other words, directly, how much of soap is actually found on the bar of soap is communicated with the total fatty matter percentage. Total fatty matter refers to the actual soap that is formed when we are carrying out a saponification reaction. So total fatty matter refers to the RCOONA that is found in soap, or in other words, the sodium carboxylate salt that is found in soap. So students, we will allow this soap to get filtered out through this Buchner funnel, and after majority of the solution, aqueous solution, has gotten separated from this soap that we have here, we can move on to shaping the soap and testing how the bar of soap that we have produced actually work. Now students, in this Buchner funnel, we have the solid soap, and we have filtered out the aqueous layer into our conical flask here. In this aqueous layer, like I have mentioned earlier, we have glycerin and sodium hydroxide mainly. So in this soap that we have here, we have a small amount of glycerin as well as water and sodium hydroxide present in this solid soap as well. So let's take the solid soap that we have in the Buchner funnel into a clear beaker so that you can observe it a bit better. We can use a spatula to scrape out the soap that we have formed. Students, make sure to remove the filter paper that was used. Now students, you can see the soap we have formed here. It is a white color solid. We can further reduce the moisture that is found in this soap by taking a few pieces of paper towels and pressing the soap that we have formed between two paper towels, or we can just press the paper towel inside and remove the water that is found here. but I prefer to take all of the soap onto a paper towel, and we can press the soap that we have formed here between two pieces of paper towel and remove as much moisture from the soap as possible. Now students, we can see we have placed our soap that we prepared on a piece of paper towel, and we can take another piece of paper towel and place it on top, and we can press it to release a bit more water that is still attached to the soap here. So we will place the second paper towel on top, and we will press it until uh, the rest of the water is absorbed into the paper towels here. As you can see, when we press the paper towel onto the soap that is formed, some of the water that is released made a wet patch on the paper towel like so. So this is indicating that the soap still has some moisture left in it. After pressing the soap that is produced here between uh, two pieces of paper towel, we can place this soap that is produced in a mold and shape this to look like more of a cake of soap or a bar of soap. So now let's transfer the soap that we have produced into a mold so that we can produce a bar of soap with the use of the soap that we have formed here. And to do that, we have a small mold that we have prepared. We can transfer some of the soap that we have prepared here into this mold, and then we can press with this lid to shape the soap that we have put in this mold into a nice bar of soap. So let's take a small amount of soap and place it in our mold here. Now, after packing it in with some soap, we can place the lid and apply pressure to shape the soap bar. And after doing so, you can remove the lid and we can allow it to settle for a while. After putting the soap in the mold, we will allow it to settle for a while, and after that we can remove it from the mold and observe the soap bar that we have produced. Students, in this experiment, we formed soap today by reacting or mixing oil with sodium hydroxide. The reaction happened here was a hydrolysis reaction where the ester bonds were broken in the triglycerides found in our soap to produce sodium salts of carboxylic acids. Or in general, we can give a general formula RCOONA. So this was referred to as soap. And after forming the soap, we were able to separate the soap from the aqueous solution, and then we placed the soap that we produced in a mold, and then we allowed the soap to solidify at room temperature for a while now. So let's take the soap bar that we have produced with the use of a mold. So in this mold we can press from the bottom and bring the soap bar up like so, and we will place it in a we can place the soap bar that we have produced in a petri dish here. So now students, we can move on to observing the nature of the soap bar that we have produced. We can see it is white in color, and the soap bar mainly contains sodium salts of carboxylic acids. But keep in mind students, when it comes to producing soap, it is not just sodium hydroxide that is normally reacted with a plant-based oil. In this case, we used coconut oil, and we reacted the coconut oil with sodium hydroxide, or caustic soda is another name for sodium hydroxide. So we used caustic soda to react with the coconut oil. Apart from that, we can actually react our plant-based oil with caustic potash or potassium hydroxide. Now, the resultant soap is a potassium salt of carboxylic acids. So it's a mixture of potassium salts of carboxylic acids, and these types of salts made with potassium tend to be softer on the skin, and therefore we find that type of salt in baby soaps. So over here we have a baby soap. This will contain potassium salts of carboxylic acids mainly. And as I mentioned earlier, different soaps have different total fatty matter percentages, or TFM percentages. So total fatty matter refers to the RCOONA, or amount of sodium salts of carboxylic acids that are found in a bar of soap. Majority of the time, a bar of soap will contain TFM percentage value of between 54% to 56%. However, depending on the soap that you are using, the TFM value might vary. If you take a look at the bar of soap that we have here, this bar of soap, which is a baby soap, or soap that is used when it comes to washing babies or anything that is involved with babies, is containing a TFM value of 78%. It's a really high TFM value. So this type of soap will have a higher washing action, or it is going to be having higher washing properties, because the higher the TFM value, the easier it will be to carry out the washing action of soap. So over here is the soap bar that we produced. As you can see, this is the soap bar that we produced. And now in this part of our practical, we are actually going to conduct a small additional part of our practical, that is trying to observe what happens when soap comes into contact with hard water. As you know students, when it comes to hard water, the soap will not produce enough foam, or we can say soap is not lathering when it comes to hard water. Now, hard water contains calcium and magnesium ions. In the presence of calcium or magnesium ion concentrations, or high concentration of calcium and magnesium ions, the soap will start to precipitate out. Just like when we precipitated soap by increasing the sodium concentration in the medium, in the presence of magnesium or calcium ions in the medium, or higher concentration of magnesium and calcium ions in the medium, you will have the ionized soap or the carboxylate ion of the fatty acids that is present in the aqueous medium of a soap solution will precipitate out in the presence of high concentrations of calcium or calcium or magnesium. To observe this, we have magnesium sulfate here. We are going to dissolve a small amount of magnesium sulfate in a little bit of water, and apart from that, we are going to take a small sample of our soap that we have produced, and we will dissolve it in a small amount of water to produce a soap solution. And we will take a small piece of soap that we have bought from a store, and we will dissolve it in water to produce a solution of soap with that baby soap we have in front of us. And afterwards, we will mix the magnesium sulfate solution with each of these soap solutions to observe how the soap will start to precipitate out in the presence of high concentrations of magnesium 2 plus ions. So let's move on to that part of our practical. Now students, first let's observe what we have in front of us. Here what we have is a soap bar that we produced, and this soap bar, the pink color soap bar, is a store-bought soap bar with a TFM value of around 78%. And then we have magnesium sulfate, and we will have to use distilled water. So in the wash bottle here we have distilled water, and we have few test tubes as well. So in this part of our practical, we'll first take a small amount of magnesium sulfate and dissolve it in water. We'll add water with the help of a wash bottle. And we can dissolve the magnesium sulfate. We are trying to make a concentrated solution of magnesium sulfate, so we can very clearly observe the action of magnesium 2 plus ions when it is added with a soap solution. There is still a small amount of magnesium sulfate that is not dissolving in this small volume of water we have taken, indicating that we have produced a saturated solution of magnesium sulfate here. So we will keep the magnesium sulfate solution here, and let's move on to taking small portions of each of these soaps that we have in front of us, and we'll try to dissolve this soap in a small amount of water. So let's take a spatula, and we'll take a small portion of the soap that we produced, and let's add water to this soap, and we will dissolve this soap as much as possible. You can see as we stir, this soap solution, it is producing foam, indicating that this soap is in fact formed properly, because otherwise, if it didn't contain enough soap, you will not be observing this foam layer that is found on top of water. Now, let's take a small piece of our store-bought soap, and we can add this store-bought soap into this beaker. Now, students, we have taken a small amount of store-bought soap into this beaker. Let's add water, distilled water to it, and mix this well and observe the formation of a soap solution. The store-bought soap produces a nice layer of foam faster than our lab-produced soap did. So, in fact, this store-bought soap actually has a high percentage of total fatty matter, TFM. So, this effortless forming that you observe is indicative of the high percentage of TFM present in the soap. We can add a little bit more water. Now, we have prepared a soap solution with the use of the soap that we produced in the lab, and we have prepared another soap solution with the store-bought soap that we have in front of us here. So that soap solution is found here. Now, students, let's take our test tubes. So again, we have our soap solution or store-bought soap solution here, and over here we have the soap solution that is made with the soap that we prepared. Let's take 2 droppers for each of the soap solutions, and now we are first going to take a test tube and add a small amount of water to this test tube, and let's add a small amount of the soap solution that is made with the soap we prepared, and observe what happens when we add soap to our water here. When we added soap to the water here, do you see the formation of a precipitate? No. So this indicates that our water that we obtained here, or the distilled water that we have here in the lab, does not contain excess amount of magnesium or calcium ions, because this is distilled water. And now, to another test tube, we are going to take our magnesium sulfate solution. If you can remember, we prepared a very concentrated solution of magnesium sulfate, and we are going to take a small portion of magnesium sulfate into our test tube, and to this test tube we are going to add the soap solution made with the soap that we prepared in the lab. So now let's add a few drops of our soap solution to our magnesium sulfate solution. As you can see, students, as soon as you added the soap solution to our magnesium sulfate solution, there was a formation of a precipitate. Did you observe the formation of a precipitate when you added the soap solution to water, the distilled water that we had in the lab? No, we did not. So over here, you can very clearly observe when we added soap to our magnesium sulfate solution, the soap formed a precipitate. You can very clearly observe the precipitate when I shake it here. You can see it is not dissolving. You can see the precipitate particles are suspended throughout the aqueous medium. So in just distilled water, you will not observe this formation of the precipitate, but in a solution that contains a high concentration of magnesium 2 plus ions, you can see soap. Now we'll keep it aside for the time being, and now let's move on to the soap that was store-bought. Now let's observe what happens when we do the same experiment with the store-bought soap. So we have a test tube. We will add a small amount of water to this test tube, and we'll add a little bit more water. And to this water, we'll be adding a small amount of soap solution prepared with the store-bought soap. As you can see, it's mainly foam that I had taken into the dropper. We'll add a little bit more soap. Now we have added quite a bit of soap into our distilled water here. Do you see the formation of a precipitate here? Do you see the formation of a precipitate here, students? You do not see the formation of a precipitate. It's just the foam that you see here. Apart from that, there is no formation of a precipitate here. Some pieces of soap has come into the medium. Apart from that, there is no precipitate formed here when we added the store-bought soap solution into distilled water. Now we are going to take our magnesium sulfate solution and we are going to add a few drops of our store-bought soap solution, or soap solution prepared with the store-bought soap. Observe whether there is a formation of a precipitate. We can see as we add the soap solution to magnesium sulfate solution, there was a formation of a precipitate. This is again because of the high concentration of magnesium 2 plus ions in the aqueous medium. The soap that is ionized here in the soap solution gets precipitated out in the presence of high concentration of magnesium or calcium 2 plus ions. So now students, if you mix it a bit more, you can see that this precipitate is not dissolving in water. This is a very clear observation that when you added the soap solution to distilled water, there was no precipitate formed, but when you add the soap solution to magnesium sulfate, there was a very clear white color precipitate formed. So due to hardness of water, we are going to observe the soap that you use actually precipitates out, and it will be difficult for the soap to lather. Students, so this is an inherent issue that we have found with soap. When it comes to using soap, if you are using hard water, the action of soap is going to be hindered, as soap will be precipitating out from the aqueous solution if the aqueous solution contains high concentrations, or if the aqueous solution contains calcium or magnesium 2 plus ions. Even if ions are also present, you can see the same type of precipitation taking place. To eliminate this issue, you can use detergents, as detergents will not start forming a precipitate in the presence of hard water, or calcium or magnesium 2 plus ions in water will not be able to precipitate out detergents. Students, this part of our experiment was an additional experiment that we did to communicate the fact that magnesium and calcium 2 plus ions in the medium will cause the soap to precipitate out again. With this additional part, we can now conclude experiment number 41. Questions and other important theory parts revolving around experiment number 41 will be discussed in the next session.
Now students, we are going to be taking a look at some questions that are associated with experiment number 41, preparation of a soap sample in the lab. So let's take a look at the first question. Glyceryl tripalmitate is a raw material that is used in the manufacturing of soap. Its structural formula is given below. So what we have is the structural formula given below. So after observing the structure, you can see over here we have the same fatty acid chain. And then the question is, what other chemicals are required for producing soap using the compound mentioned above? So students, when preparing soap, whenever we have triglycerides, we need to break this ester linkage that we have over here, and we use sodium hydroxide for this. So we need to mention the chemicals that we'll be needing for this experiment, right? And when we are preparing soap, usually after the preparation of soap, to neutralize the excess sodium hydroxide that is present in the medium, we'll be using acids like stearic acid or phosphoric acid. So after adding sodium hydroxide, to remove the excess sodium hydroxide present in the medium, we'll be using acids such as citric acid, phosphoric acid, or even free fatty acids found in oils like coconut oil can be used for this purpose. So you have to keep those in mind. Write balanced chemical equation for the formation of soap using the compound mentioned above. So we have to be able to write a balanced chemical equation for the saponification reaction that is taking place. After dissolving soap sample in water, subsequently adding calcium chloride, what observations can be made? So after dissolving soap sample in water and subsequently adding calcium chloride, what observations can be made? So we are going to take a look at what happens with the addition of calcium ions into a soap sample, and name a type of fat or oil that can be used for manufacturing soap apart from the compound that is mentioned above. So apart from this mentioned glyceryl tripalmitate, is there any other oil or fat that we can use to produce soap? So while keeping these questions in mind, we can now move on to answer each one. What other chemicals are required? What other chemicals are required to prepare soap here? So when it comes to producing soap using the compound above, now we already have been given a triglyceride here. So we have to carry out alkaline hydrolysis. So we will be using sodium hydroxide, or you can use potassium hydroxide if you wish, or any strong base like this. Sodium or potassium hydroxide is going to be the ones that are preferred. So we use sodium hydroxide or potassium hydroxide. And then apart from that, we can also use acids like citric acid or phosphoric acid. We'll include phosphoric acid here. Right, apart from phosphoric acid or citric acid. Now, the addition of phosphoric or citric acid is done to remove the excess sodium hydroxide that is going to be remaining in soap after the soap has been produced. Now, when we add sodium hydroxide to produce sodium salts of fatty acids, that is what is known as soap. And this process is known as saponification. And after the saponification process has been done, there is going to be excess sodium hydroxide in the medium. So to remove this excess sodium hydroxide, we are going to add an acid like this, so that it can react with the excess sodium hydroxide and remove the excess sodium hydroxide in the medium. And after this, students, actually apart from this, we can also use solvents like ethanol. As you know, these fatty acids or these triglycerides that are present here are not very miscible with aqueous solutions of sodium hydroxide. So as a solvent, we can use ethanol as well to make sure the two solvents to reactant will mix together. So the fatty acids or these triglycerides, so triglycerides and aqueous solutions, they don't mix well together, so we will use a solvent like ethanol to make sure it acts as a co-solvent and allow the reactants to come into contact with one another really well in the process of preparing soap. So we can also use ethanol as a solvent. Right, so these are the main ingredients we'll be needing. Apart from this, students, if you are manufacturing soap in an industrial setup, apart from this, you'll be adding coloring agents, fillers, preservatives, and fragrances so that it has a pleasant smell. So, and majority of the time, all the industrially bought soaps do not contain 100% soap. So we know something called TMF values there, total fatty matter, that indicates the amount of sodium salts of fatty acids that are present in the bar of soap that you buy. So they are normally around 54 to 56. Sometimes certain soaps it goes up to around 70, but majority of them are around 54, 56%, meaning or indicating that you have added a lot of other additives such as fillers, preservatives, coloring agents, and fragrance particles. So those material will be needed when you're preparing soap at an industrial setup to produce it as a product to supply to the market. Write the balanced chemical equation for the formation of soap using the compounds mentioned above. Right, so we have to be able to write the saponification reaction now. CH2O, C double bond O. Then we have CH214, CH3. Now this is the fatty acid group, and then we will complete the triglyceride here first. So this will produce, first of all, we'll identify what the acid section is so that you are also clear about what is taking place here. So a triglyceride is a product that is produced when glycerol molecules react with fatty acids. And fatty acids and glycerol, when they react together, the linkage that they form is known as a ester linkage, or what they form over here are ester bonds. So all of these that I highlight are the bonds that are going to be broken in the presence of sodium hydroxide, and these are our ester bonds. And when these bonds are broken, you would normally, this is called a hydrolysis process, and at that point you will form a carboxylic acid anion, because since this is happening in alkaline medium, you don't directly form the carboxylic acid of this fatty acid. Instead, you form the carboxylic acid anion. And over here, you will form the glycerol molecule. So the products would be the glycerol molecule along with the carboxylic acid anion, or in this case, since the carboxylic acid happens to be a fatty acid with a long carbon chain, we can say fatty acid anion is formed. So we have in the medium sodium plus ion, so we can say fatty acid sodium sols are formed. CH3, CH214, C double bond O, O minus, and Na plus. Now, this is the product that we refer to as soap, sodium sols of fatty acids. Sodium sols of fatty acids, and you will be forming 3 of them. And apart from that, you will be forming glycerol. So these are the main products that are going to be formed. So since we need to balance this equation, we will have to add 3 in front of sodium. Now the equation is balanced. So students, this equation or this reaction that is taking place is referred to as a saponification reaction. And as you can see, if you make it smaller, as you can see, these triglycerides react with sodium hydroxide, and as they react, there's a hydrolysis that is taking place. When these carbon-oxygen bonds, they break, and since this hydrolysis is taking place in the presence of sodium hydroxide, which is a base, the product that is formed is our fatty acid sodium salt. So since it's a basic medium, the product that is formed is a sodium salt of the fatty acid. If this hydrolysis was done in acidic medium, instead of forming this, you will be forming a fatty acid, not a sodium or potassium salt of a fatty acid. Instead, you will be forming the fatty acid. So the ending would be COOH. So since this is happening in alkaline medium only, you will be getting these sodium salts of the fatty acid, which is referred to as soap. Right, let's move on to the next question. After dissolving soap sample in water and subsequently adding calcium chloride, what observations can be made? So students, when a soap sample is dissolved in water, so we have CH3, CH214. We'll take the same soap sample we prepared earlier. We have this soap sample. So if you dissolve this soap in water, then you will be forming these ions CH3, CH214, COO minus, carboxylate anion or fatty acid anion is going to be formed. Apart from that, sodium 1 plus ions are going to be formed. These are all in the aqueous medium. Now soap is dissolved in water. However, in the presence of calcium, these anions that are formed can react with the calcium 2 plus ions that we have added into the medium and can form a precipitate.
So we have CH3, this same anion is going to be, actually in this case we don't have to include the negative sign here. So the calcium salts of these fatty acids, are not water soluble. You experience this when you use hard water to wash your hands with soap. So if you take hard water and try to use soap along with hard water, you will see soap is not lathering, or there's no bubble formation in soap. Instead, a thick white layer might get formed on your hands. So this is because the soap that you're trying to dissolve is not necessarily dissolving in the water you are using, as the water is hard. Hardness of water is there due to the presence of high concentrations of calcium or magnesium ions. So in the presence of calcium or magnesium ions, these fatty acid anions can react with the calcium or the magnesium ions to form a precipitate. So unlike the sodium salts of fatty acids, calcium magnesium salts of these fatty acids are not soluble in water. So what happens is, students, they form a white precipitate. So this precipitates out as a white precipitate. And this is also referred to as soap scum. Actually, this prevents the action of soap. It prevents the washing action of soap. This is one of the problems we have when we're using soap along with hard water. So in areas, in dry regions of the country where there is a lot of hard water, the use of soap like this would be problematic, because soap cannot show its washing or cleaning action because of the precipitation of the soap molecules in the presence of hard water. In the presence of hard water, the fatty acid anions will precipitate out as a white color precipitate. So this is the reaction that takes place when you add a soap solution with calcium chloride or any salt containing magnesium ions or calcium ions. Okay, so the answer to this question is that what observations can be made? The formation of a white color precipitate is going to be our observation. Name a type of fat or oil that can be used for manufacturing soap apart from the compound that is mentioned above. So students, we can use plant oils or animal fat. Either one can be used to produce soap. Any plant or animal fat would contain triglycerides. Especially plant oils are used for the manufacturing of soap, and all the plant oils contain different types of triglycerides. All of these triglycerides can be used for the manufacturing of soap. However, keep in mind, apart from the triglycerides, certain plant oils will have small quantities of free fatty acids as well. Fatty acids that are not joined to a glycerol molecule. So now, what are the other oils that are mainly in use? We have to just name one. We can mention we mostly use coconut oil for this purpose. So we can write coconut oil can be used. Right, apart from that, many other plant oils, vegetable oils can be used for the preparation of soap. Each of these oils will contain triglycerides that can undergo alkaline hydrolysis or saponification process
to produce soap. Now let's take a look at the next question. So we are now with the second question. A triglyceride forms through the reaction involving the compounds provided below. We have lauric acid and glycerol. Write the balanced chemical equation for the given reaction. So when lauric acid reacts with glycerol, so this is a fatty acid. When this fatty acid reacts with this glycerol molecule, what can take place? You can form a triglyceride. The triglyceride made above is trilaurate. Using trilaurate as a starting compound, what other chemicals are required for the production of soap? So when it comes to soap production, what other chemicals are required? So we can list them down and then state 4 main steps of soap manufacturing process. Explain the soap manufacturing process through these 4 steps. Utilizing glyceride formed in part 2 of the question, outline compounds are required to form the production of biodiesel. Now students, keep in mind, now we are forming a triglyceride here. So using that particular glyceride that is formed here, they are asking us, how can we form biodiesel? We learned about biodiesel as well. So here in this case, we are going to briefly outline the process of manufacturing biodiesel starting from a triglyceride. Write balanced chemical equations for the production of biodiesel from the compounds stated above. Right students. So now we are going to move on to writing the answer to the first question. We are asked to write a balanced chemical equation for the given reaction where lauric acid reacts with glycerol. So glycerol and lauric acid, glycerol and lauric acid can react to form a triglyceride. So we have our glycerol molecule. To very clearly show which OH groups and which hydrogens are going to react with one another, I will write this acid not in the form that is written here, but I will have to rotate it to bring the COOH groups over here so that you are going to be very clear about the reaction that is taking place. And I will use a different color so that you have a better understanding of how these two acids and in this case the glycerol is joined together through a ester bond. Right, so we have our acid molecule. So this is the same acid as the acid that is given here. Keep in mind. So normally when you're trying to write the balanced chemical equation, if you write 1 glycerol and 3 of these by indicating that we are using 3 over here, that is enough. But just to show how the reaction takes place, I will repeat these 3 more times. So now students, now these are the reactants that are going to be added. And when they react, the hydrogen from alcohol will be removed along with the OH group from carboxylic acid. And the carbon over here with a double bond will join to the oxygen over here of the alcohol. and therefore will form an ester. So of the glyceride or of the glycerol molecule, these sections will remain, and the rest of the triglyceride will be made up from our fatty acid. Okay, so now this is the triglyceride that we form. This is also known as trilaurate because we started with lauric acid. So this is also known as trilaurate. Just like when it comes to tripalmitate, we had palmitic acid joining with a glycerol molecule to form tripalmitate. Here we have lauric acid with glycerol reacted together to form trilaurate. So as a catalyst, we can use concentrated sulfuric acid, and apart from that, you will also form a water molecule per each bond that is formed. So you will see the formation of 3 water molecules. So this is the balanced chemical equation. This is going to be our balanced chemical equation, students. Here, concentrated sulfuric acid is going to be used as a catalyst, and you can see the hydrogen from the alcohol and the OH group from the carboxylic acid. In this case, we have a long chain carboxylic acid, which is also referred to as a fatty acid. So you can see the fatty acid OH group along with the hydrogen from the alcohol will be removed, and between the oxygen of the alcohol and the carbon of carboxylic acid group is going to join, forming our ester link. So therefore each of these what you see here is a ester link forming a ester over here. So triglyceride that is formed over here is an ester. Right, students. So with that, we can move out of this question. So this is the answer to the question that is asked here. The triglyceride above is trilaurate. Using trilaurate as a starting compound, what other chemicals are required for the production of soap? What other chemicals are required for the production of soap? As we know, we would need sodium hydroxide, or if you prefer, we can use potassium hydroxide. We can use phosphoric acid or citric acid. So this is to neutralize the excess sodium hydroxide that is present in the soap sample. Apart from that, we can also use fillers. You will also need, before adding the citric acid or phosphoric acid, we would need a brine solution, students. We would need a brine solution. So we will list that down here. We will need a brine solution, NaCl, concentrated NaCl solution. So you would need a brine solution. In the first question we did as well, you would be needing that. So over here, in the first question we did, over here we would be needing a brine solution as well. One of the most important things, right? The reason why we need brine solution is, students, because when it comes to the use of a brine solution, or when it comes to preparing soap, some soap that is produced can dissolve in the aqueous medium, and we would not be able to precipitate the soap that is dissolved in the aqueous medium of the reaction mixture without the help of the brine solution. Brine solution actually increases the sodium ion concentration and pushes the equilibrium towards forming soap in the solid form and not in the dissolved form. So therefore, brine solution is very important when it comes to precipitating the soap that is produced. Then we would need phosphoric acid or citric acid to neutralize the base that is present in the medium. We can use fillers. We can use coloring agents. We can use preservatives. And apart from that, we can also use perfumes. Now, these are mainly used when we are producing soap in an industrial setup. We will be using these as well. We will be adding it to the soap that we produce to produce a final product or final finished product. So these are the other chemicals that are needed for the preparation of soap. State the 4 main steps of soap manufacturing. Explain the soap manufacturing process through these 4 main steps. So now students, you should know the 4 main steps that are involved in soap manufacturing. We have saponification, and then we have removal of glycerol, then we have purification, and finally finishing. So let's go through each of these steps once more, like we did in the theory part discussion, and explain what should be written under each of these. So when it comes to saponification step, you have to mention a plant oil or animal fat is taken, which consists of triglycerides, and we are going to react this plant oil or animal fat at a temperature of around 70 degrees Celsius with sodium hydroxide or potassium hydroxide. In this process, we are forming 2 main products. One is glycerol, the other one is our soap. Soap is basically sodium or potassium salts of our fatty acids. So students, keep in mind when you mix the 2 reactants together, sodium hydroxide and the plant oil, it is not going to mix, so you have to continuously stir so that these 2 reactants come together and form the soap and glycerol products that we expect to produce through these steps. So that is the saponification step. And then when it comes to removal of glycerol, in this step, students, after the formation of soap, we know some amount of soap that got produced through the reaction has now dissolved in the aqueous layer. Apart from that, the glycerol that is produced is soluble in the aqueous layer, so it has dissolved in the aqueous layer as well. So in order to separate the soap that is produced, there will be some soap that is produced as a solid as well, but some of the soap will be dissolved in the aqueous layer. So to remove this soap from the aqueous layer, we are going to be adding a brine solution. So when we add brine solution to our reaction mixture, now it is considered to be a product mixture. So when you add our brine solution, the dissolved soap will precipitate out as our soap. This is due to the equilibrium that we see. For example, if this is our soap molecule that is produced in aqueous medium, it shows an equilibrium. So the soap produced can dissolve in water, producing this equilibrium. And these will be aqueous. This is also aqueous. So students, when we add brine solution into the medium, as we can see, sodium chloride, when we add it into solid sodium chloride, when we add it into an aqueous medium, we will see the formation of sodium 1 plus ions along with chloride ions. So sodium 1 plus ion concentration increases when we add a brine solution into our product mixture after the saponification process. So sodium ion concentration will increase quite drastically, causing this equilibrium to be shifted to the left and produce more and more of soap in the solid state. So that means soap will be precipitating, or dissolved soap in the aqueous medium will now turn into a solid and will separate from the aqueous medium. So that is why we need the brine solution. So at this point, you can see we have our aqueous layer that we can remove. It is now not going to contain a lot of soap dissolved in it because of the addition of brine solution. And due to this, if you remove the aqueous layer, majority of the glycerol along with the aqueous layer can be removed. And afterwards, students, we can move on to the purification process. So the soap that is now separated out still contains a lot of excess sodium hydroxide that we have added into the medium. Actually, a certain amount of sodium hydroxide will still be present in the soap that we have separated out. So to remove this sodium hydroxide, we can add an acid like citric acid or phosphoric acid, or even free fatty acids that are seen in plant oils can be used. So at that point, the excess sodium hydroxide will be neutralized and the pH of the soap will be brought down to a level that is not harmful for human use. So after the purification process, we move on to finishing. So when it comes to finishing, students, we take the soap that is produced. It still has a lot of moisture in it. So to remove this moisture, we will heat the soap up to about 120 degrees Celsius, and then we will spray it into a low pressure chamber. So due to this process, when we spray it into a low pressure chamber, small droplets of soap that is produced will have some water in it. So all of this water will evaporate and the soap will dry out and will get collected at the bottom of the container. And soap that is produced here is going to be in the solid form, and we can collect this soap. Now has very low amount of water in it. Now it is dry. So we take this dry soap and we can add to it things like coloring agents, preservatives, fillers, and perfumes to make our final product. And after that, we will mold them into shape and we'll pack them and be sending out to the market. So that is how we will be doing the finishing of soap. So these are the 4 main steps that we can see in the manufacturing process of soap. So now we can move on to the next question. Utilizing the glyceride formed in part 2 of the question, outline the compounds required for the production of biodiesel. Now students, we also know that we can use plant oils to produce biodiesel. And even in plant oils, what we have is mainly the triglycerides. So here in the second part of our question, we have produced a triglyceride with the use of lauric acid and glycerol. And the produced triglyceride was also referred to as trilaurate. And they're asking us now how we can produce biodiesel with the use of this triglyceride we produced earlier in question number 2. So we'll get on to it now. We have the triglyceride that we produced earlier. We'll first of all write it down. And we are going to be reacting this with methanol. We'll be needing 3-methanol, and we'll be using sodium hydroxide as a catalyst, and we'll be heating the mixture up as well. And when we do that, we are going to be producing these. If you use a different color at this point, it will be much clearer to you. So we will use a different color over here and here. So we will use red here to write methanol, and over here you will see another red color part coming into the picture. I will explain that to you in a while. Apart from that, we'll be also forming glycerol. So these are the main products that are formed starting from these reactants. Now let's observe what is taking place here. This is a triglyceride, also referred to as an ester. As you know, there are ester bonds present over here. So each of these bonds that I mark are ester bonds. So in the presence of sodium hydroxide, these bonds can break, and since we have methanol in the medium, again another ester can be formed. At this point, what is actually happening is, students, is you break one ester that we have over here, and then we exchange the alcohol part that we have when it comes to forming this ester with a different alcohol part. So at that point, students, you will form a different ester. Even this over here is an ester bond. So you can see over here the alcohol section that is making up the ester is a OCH3 group, or we can say that it is stemming from a methanol molecule. That's why we drew it in a different color. And when it comes to each of these esters, the alcohol section was stemming from our glycerol molecule. And with the addition of sodium hydroxide and heating in the presence of methanol, what we did was
we converted one ester into another type of ester. This process is known as a trans-esterification process. This is known as a trans-esterification process. And what we have formed over here, is our biodiesel. We will write it over here. So what we have formed over here is our biodiesel. Biodiesel. So biodiesel is also referred to as a mixture of fatty acid methyl esters. So these are esters due to the presence of this methyl group over here. This is a methyl group. So these are, and this entire section is a fatty acid group. So this ester can be referred to as a fatty acid methyl ester. In short, or it is abbreviated to FAME. It is abbreviated to FAME, fatty acid methyl esters. So you can see this section of the molecule. This section of the molecule, the blue section of the molecule, stemmed from a fatty acid. It stemmed from a fatty acid. And this section came from methanol, and this is a methyl group. And here what you have is a ester linkage, and this entire molecule is an ester. That's why we call it a fatty acid methyl ester. So biodiesel is ideally fatty acid methyl esters, and what we have done over here is taking the trilaurate triglyceride molecule that we have formed in question number 2 and added it with methanol and reacted it in the presence of sodium hydroxide and heat, and we produced biodiesel and glycerol. And glycerol and biodiesel will separate into 2 layers, so we can separate glycerol and biodiesel separately. And biodiesel is going to be referred to as a mixture of fatty acid methyl esters. I hope that is clear to you now. So now let's move on to the next question. Write the balanced chemical equation for the production of biodiesel from the compounds stated above. Actually, students, over here we have done that part. In this particular question, they are asking us to outline the compounds required for the production of biodiesel. So we have to outline the compounds as methanol and sodium hydroxide. Methanol and sodium hydroxide apart from the ester that is given here. So we will briefly mention what we need to do here. We have to have our trilaurate, apart from that we can also indicate the other reactants that we'll be using. Now in this case we do not have to go through the same process that we used in the previous slide, because here I'm just writing the balanced equation. I'll be just writing the balanced equation.
So this is going to be the balanced chemical equation. So let's take a look at the balanced chemical equation over here. So we have our trilaurate triglyceride reacting with methanol. There will be 3 methanols needed for this particular reaction that is taking place. And then when you do that, you'll form 3 of these methyl esters, right? And apart from that, glycerol will also be formed. So these are the products that are going to be formed from these reactants we have over here. So now it is time for us to move on to the next question. What is meant by the TMF value in soap? As I mentioned earlier, in different soap products, you will see, if you observe the label, it mentions something called the TMF value. So what is meant by the TMF value in soap? What are the raw materials needed for the manufacturing of soap? So we know the raw materials that we need a plant oil. Apart from that, we need sodium hydroxide, right? In the process that happens after saponification, we'll be needing some other different products as well, like the brine solution. We'll be needing citric acid or phosphoric acid, right? So, and then after that, in the finishing process, we'll be needing different other chemicals as well. So we are aware of the materials that are needed for manufacturing of soap. What is known as soft soap? So when it comes to soft soap, students, soft soap is basically soap that is a bit more gentle on the skin, especially used for the washing purposes or washing of infants or babies. So this is also commonly referred to as baby soap. So soft soap is going to be produced with the use of potassium hydroxide, and this type of soap is going to retain a little bit more moisture than the other soaps, and potassium salts of carboxylic acid based soap that we use over here is known to be more gentle and less harsh on the skin. State the intermolecular interactions that a soap molecule can make with water and dirt particles, and then describe the methods that can be employed to lower the high pH of soap resulting from excess sodium hydroxide, making it suitable for human use. So when it comes to the purification process, we explained what we will be doing to remove the excess sodium hydroxide in soap. So the answer to this question is what we discussed under the purification step of manufacturing soap. What is meant by the TMF value? TMF value stands for total fatty matter. Total fatty matter. So total fatty matter stands for the amount of soap that is actually present in the soap bar. As we have observed before, in the final step of manufacturing soap industrially, in the finishing step, apart from soap, we have other things that is added to the soap. So therefore, if you take a bar of soap that is not 100%, our sodium salts or fatty acids, there are other things added to it to make it more marketable and to make it more pleasant to use. So, and to make sure that it lasts for a while. And students, you have the soap content in it communicated with the use of TMF value, total fatty matter. So students, usually in a soap bar, the total fatty matter content may vary from around 54% to 56%, but there are certain soaps that even has a fatty matter content that is exceeding the 70% value as well. So TMF value stands for the total content of sodium salts of fatty acids, or in other words, total content of soap in a given soap bar. What are the raw materials needed for the manufacturing of soap? We will need plant oil or animal fat, without them we can't carry out the saponification process. So another very important ingredient for the saponification process is sodium hydroxide, right? So the saponification process requires sodium hydroxide, or you can use potassium hydroxide as well. And in the removal of glycerine step, we'll be needing our brine solution, which is concentrated sodium chloride basically. And apart from that, in the purification step, we'll be needing citric acid or phosphoric acid. Citric acid or phosphoric acid can be used. And after the purification process, now purification process is where we remove the excess sodium hydroxide. So after that process, in the finishing steps, we can add fillers, coloring agents, preservatives, and perfumes. These can be added. Right, so these are the main raw materials you'll be needing for manufacturing of soap. What is known as soft soap? We can write soft soap is soap manufactured using KOH as the base. Here the potassium source of fatty acids formed are known as soft soap. Now, what is the reason for calling these soft soap? Now, this soap that is produced is gentle on the skin, and apart from that, the moisture content that is retained in such a soap bar is slightly higher. So, due to these reasons, it is referred to as a soft soap. And due to the fact that it is gentle on the skin, we use this for washing purposes that revolve around babies and infants. So therefore, this is referred to as baby soap as well. This is referred to as baby soap as well. So now let's move on to the next part. State the intermolecular interactions that a soap molecule can make with water and dirt particles. Now, for an example, since we have been looking at different types of soap molecules that are formed, we can take a look at the type of soap molecules that are formed when trilaurate is has undergone saponification. So at that point, you will form this type of soap molecule, CH3, CH2, 10, C11O, O minus, Na plus. So this is a soap molecule that is formed when trilaurate undergoes a saponification process. So now let's take a look at the skeletal structure to have a better understanding of what is going on. So you can see over here, students, there are 11 carbons here, and with this carbon it will be 12 carbons. So if I draw its skeletal structure, it's going to look like this. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So over here also we have 11 carbons, and this is going to be our 12th carbon. So on the 12th carbon we have a double bond. On the 12th carbon we have a double bond with oxygen here, and then oxygen over here. Along with that we have Na plus. Now if you take a look at this molecule, we can see that only this part of the molecule appears to be polar, and the rest of the molecule, the entire rest of the molecule from all the way here to here, is a hydrocarbon section. This is non-polar. This is non-polar. We say this is a hydrophobic section. Why? Non-polar section does not like to interact with polar substances, and water happens to be polar. So this is non-polar. Does it interact well with the polar molecules that we have in water? No. So therefore we say this section is a hydrophobic section. So we actually say this part is the hydrophobic tail. Hydrophobic tail. And the polar section likes to interact with water because water is also polar, and like dissolves like. So therefore polar section will have strong interactions with the polar solvent water. So this section is referred to as hydrophilic. Hydrophilic head. Hydrophilic head. So we say when it comes to a water molecule, we have a hydrophobic tail and a hydrophilic head. Hydrophobic tail and a hydrophilic head. So students, now if you draw it as a small diagram, we can see we have a hydrophilic head followed by a hydrophobic tail, followed by a hydrophobic tail. So when it comes to a soap molecule, it contains one section that will form strong interactions with polar solvents like water, and another section that will form interactions with non-polar substances like dirt particles. So this will move on to the question again. The question asks us, state the intermolecular interactions that a soap molecule make with water and dirt particles. So at that point, students, you'll have to write the answer in the following manner. You'll have to write, if you take water, let's say this section is water, this area is water, and this part is dirt. In the soap molecule, the hydrophilic head section will dissolve in water and the hydrophobic tail section will dissolve in dirt. And since this tail section is hydrophobic and it is mainly consisting of carbon and hydrogen, and dirt is mainly things like grease or oils come together, so therefore dirt is also going to have mainly non-polar substances, and between non-polar substances and this non-polar tail you're going to have mainly London forces, or we can say induced dipole interactions can be seen over here, or in other words you can write London forces of attractions are mainly going to be observed when it comes to the tail section of the soap molecule and the dirt particle. So when it comes to the interactions between tail section of the soap molecule and dirt particles, you are going to see London forces that are being formed. And when it comes to polar head section of the soap molecule, it is capable of forming dipole-dipole interactions as well as hydrogen bonds. It can form dipole-dipole interactions as well as hydrogen bonds with the water molecules. So since we have oxygens here which is going to be carrying a partial negative charge, and when you are talking about water molecules, there are hydrogen atoms that are carrying partial positive charges. So between these two you can have interactions formed which will be named hydrogen bonding. So therefore, if you are talking about water molecules, soap molecules, hydrophilic head is capable of forming hydrogen bonds with water molecules. When it comes to other substances, it can form dipole-dipole interactions if the other substance is a polar molecule. So therefore, students, the answer to this question is that when it comes to the hydrocarbon section, it can form London forces of attraction, and when it comes to our hydrophilic head section of the soap molecule with water, it can form hydrogen bonding. Right, students. So now we can move on to the next part. Describe the methods that can be employed to lower the high pH of soap resulting from excess sodium hydroxide, making it suitable for human use. So we know there will be small quantities of sodium hydroxide that is still remaining in the soap sample before the purification step. So in the purification step of soap manufacturing, we use something like citric acid, or phosphoric acid, or free fatty acids. We can say free fatty acids from coconut oil can be added to neutralize the excess sodium hydroxide that is present in the soap sample. So students, when we add this acid to our soap sample, if there is any residue of sodium hydroxide, it will react with these acids and will neutralize the base. So therefore, students, the high pH that is present in soap due to the presence of excess sodium hydroxide can be lowered with the addition of these acids. So the pH is lowered mainly due to the fact that sodium hydroxide present in the soap sample is now neutralized with the use of these acids that are listed here. Right. So describe the method. So we can say in the purification step of soap manufacturing, we are going to be using these acids, or one of these acids can be used for this purpose. We are going to be using these acids to neutralize the excess sodium hydroxide and thereby decreasing the pH of the soap that is produced.
So this actually happens in the purification process. Now we move on to the next question. What is the main byproduct? What is the main byproduct of soap manufacturing process? What is the main byproduct of soap manufacturing process? So students, when it comes to manufacturing soap, we are using triglycerides and then we react it with sodium hydroxide. Soap is basically the sodium source of the fatty acids we make. And apart from that, when the triglyceride breaks into fatty acid salts, the other part that is produced is our glycerol molecule, also referred to as glycerine. So this glycerol that is produced has a real commercial value. We use it in many different products. We will be talking about that in other parts of this question. So the main byproduct that is produced here when you are carrying out the saponification process is glycerol. What are the other industries that use this main byproduct? Yes, there are many other industries that use this main byproduct. Actually, glycerine is more valuable or more expensive than soap that is produced. And glycerine is used in industries such as cosmetic industry. Apart from that, we use it to produce certain explosives like trinitroglycerine. And apart from that, it can also be used in the manufacturing of different medicines. So when it comes to the pharmaceutical industry, we will be using these byproducts. What is the type of reaction that takes place in the soap manufacturing process? So in other words, when we are talking about saponification process, what type of reaction is our saponification process? What type? So we will be explaining that over here. We know we are basically taking the triglyceride and we break the ester bonds that are seen in the triglyceride. So you might have an idea what type of reaction that is by now. So we'll talk about that in that question. And then mention the uses of sodium hydroxide. So why do we use sodium hydroxide? For what purposes are we using sodium hydroxide is explained over here. So now let's move on to the next part. What is the main byproduct of soap manufacturing process? The answer is glycerol. And if you give the formula, that is CH2OH, and you can see there are two other OH groups present in the same glycerol molecule. So this is our glycerol. What are the other industries that use the main byproduct mentioned above? So we use glycerol when it comes to manufacturing cosmetics. So we use it in the cosmetic industry. We will be using when it comes to manufacturing explosives. Mainly TNG. Now TNG stands for trinitroglycerine. Trinitroglycerine. And then when it comes to producing different types of medicine. So in all of these three industries and more actually, we'll be using glycerine. So students, when they ask you what are other products or what are the industries are using this main byproduct glycerine or glycerol, you can actually list them down. Cosmetics, explosives, and medicines can be produced through the use of glycerol. What is the type of reaction that takes place in the soap manufacturing process? So just to give you an idea again, so we have our glycerol molecule connected to
a fatty acid, right? So each OH in the glycerol has reacted with a fatty acid and finally has formed a triglyceride. If you indicate the triglyceride molecule in this manner, so R will stand for a long carbon chain or long hydrocarbon chain. So these are fatty acids that we have indicated over here. So when we react it with sodium hydroxide, you will observe that these bonds that we have over here, these are called ester bonds. These ester bonds will break. So whenever you are carrying out a reaction with the use of sodium hydroxide or even an acid and break bonds, we call them hydrolysis reactions. In aqueous medium, if your acid or a base is used to break such bonds, we can actually refer to it as a hydrolysis reaction. This is a hydrolysis reaction, students. So in this hydrolysis reaction, you are going to be producing carboxylic acid anion along with, since we use sodium hydroxide, sodium ions will be along with the anion. Apart from that, glycerol will be formed. So this is the main byproduct as explained earlier. So after observing the products and in what type of medium this reaction has taken place, we can further be specific about the type of reaction that happens here. This reaction is happening in alkaline medium. So this is not just any hydrolysis reaction, we call it hydrolysis that is done in alkaline medium. You can write alkaline hydrolysis, alkaline hydrolysis of an ester. So what happens here, the type of reaction that is taking place here is an alkaline hydrolysis of an ester. You can see these ester bonds are broken in the presence of sodium hydroxide base, and we produce sodium salts of the fatty acid along with glycerol. And since we did this experiment, or since we did this process in alkaline medium, this is referred to as an alkaline hydrolysis. If we carry out the same reaction acidic medium, it will be acidic hydrolysis. At that point, if you carry out this reaction in acidic medium, instead of having a COO group, you would normally observe the formation of COOH group. That is the only difference in a alkaline and acidic medium. In an acidic medium, you will have this section produced over here, and in an alkaline medium, you will have the carboxylate anion formed. So carboxylate anion along with the sodium ions present in the medium has formed our soap molecule, which is known as sodium salts of the carboxylic acids, or sodium soaps of fatty acids. So students, this process you have to mention is a alkaline hydrolysis of an ester. That is the type of reaction we observe over here. And then mention uses of sodium hydroxide. So sodium hydroxide can be used, in the manufacturing process of soap, right? Manufacturing process of soap, used in the manufacturing process of soap. And used in the manufacturing process of biodiesel.
We use sodium hydroxide as a strong base in the lab. Used as a strong base in So when it comes to laboratory setups, when it comes to doing titrations and all that, we will be using sodium hydroxide as a strong base required for many other reactions as well. Used as a cleaning agent. Used in the manufacturing of bleach. So these are some of the uses of sodium hydroxide. Right, students. So now we can move on to the next part. So let's take a look at the fifth question here. If a soap sample contains residual sodium hydroxide and calcium nitrate and magnesium nitrate are provided to you in a laboratory setup, propose a method to determine the sodium hydroxide content in the soap sample. Now this is a very interesting question. Now let's imagine we have a soap that is provided to you, right? We have a soap sample, or we can say just we have been provided a soap. We have a soap bar, right? Now we have to determine its sodium hydroxide content. So students, first what we can do is we can scrape off, or we can take a small sample of soap from the provided soap bar and make sure that we measure and obtain the correct mass of the soap that we use. For example, let's say we take about 5 grams, right? And after preparing our soap sample, basically you can scrape the soap and take a small amount of soap into a wash glass and you can weigh it. Now the reason why we have to scrape it and take it, students, like whole chunks of soap will not easily dissolve in water, but if you have turned it into tiny particles, it will easily dissolve in water. And then we can dissolve this in a known volume of water and prepare our soap sample, or soap solution actually. So after preparing our soap solution, now we are provided with, very clearly they state, we are provided with calcium nitrate and magnesium nitrate. We can use either one for this purpose. Now as you know, soap in aqueous medium exists as fatty acid anions and sodium ions, and the fatty acid anion in the presence of calcium ions or magnesium ions can precipitate. In the presence of calcium ions and magnesium ions, it precipitates, and we have learnt about this in the theory parts as well as some of the questions we did here today. So then what happens? Now we cannot carry out our sodium hydroxide related titrations while the soap is present in the medium. It will interfere with the titration. So we will be removing the soap that is present over here, and we can do that by adding excess calcium nitrate.
So if we had excess calcium nitrate, at that point, students, you will see in our soap solution, a white color precipitate will be formed. This white color precipitate that is formed is our calcium salts of fatty acids, or in other words, we also refer to as a soap scum, which is a white color precipitate. A white color precipitate will be formed, and this is also referred to as soap scum. And then we can filter. This setup. We can use gravity filtration and obtain, actually we can directly filter it into a titration flask. We can directly filter it to a titration flask, and we can obtain the filtrate. So all of the white color precipitate will remain here, which is going to be our soap scum. And now in this solution, there is no soap, only whatever that was present in the soap, except for the soap contained, will be there. So all of the soap that was present in this 5 grams of the soap bar that we scraped off is now precipitated as our white precipitate. So normally we know in a soap bar, we don't only have soap, we have other substances as well, and having some amount of sodium hydroxide is also possible. So as we know, students, if you take a soap bar, the TMF value is around 55, 56 or 54 to 56. So students, that means other substances are also present. So when you measure 5 grams of our soap, that doesn't mean it contains only our sodium salts of fatty acids. So sodium salts of fatty acid is what is actually referred to as soap. The industrial product that we refer to as soap contains other substances as well. But when you take 5 grams over here, it is containing our sodium or potassium salts of fatty acids. Apart from that, some other substances can also be there. And when we dissolve it in water, all of them will dissolve in water. And when we add calcium nitrate or magnesium nitrate in excess, what happens is all of the fatty acid anions will precipitate out. All of the fatty acid anions, or in other words, the actual soap, will precipitate out, leaving behind any other water-soluble substance in this supernatant. So when we filter it out, the filtrate will contain any other substance that was there in soap. So if sodium hydroxide was present here, sodium hydroxide will be present in the medium in this filtrate. So this is a base. This will show a clear reaction with an acid. So we can now proceed to carrying out a titration. So finally, a titration can be carried out with the use of HCl and phenolphthalein indicator. So you can add the phenolphthalein indicator here, right? So we have our sodium hydroxide. So imagine we have added our phenolphthalein indicator here. So then this will be pink in color, and we can carry out a titration with the use of an HCl solution with a known concentration. Right, concentration should be known of the HCl solution, otherwise we can't figure out how many moles of sodium hydroxide was present in this volume. So if you find out the number of moles of sodium hydroxide that is present here, and at that point we can find out the number of moles of sodium hydroxide that was present in this entire mass of soap. Okay, students. So if you have let's say X amount of sodium hydroxide here, if you have X amount of sodium hydroxide here, then it is present in 5 grams of soap, then we can figure out in the main soap bar how many moles of sodium hydroxide is present. So this is the process. This is the process that you will use to determine the sodium hydroxide content in the soap bar. Or you can, if you want to communicate it as a percentage, you can do this as well. So this is how you would usually carry out the reaction. So you have to write down, students. You will take a known mass of the soap sample, dissolve it in water, and you will add to that solution excess calcium nitrate or excess magnesium nitrate. Then this will precipitate the fatty acid anions as calcium or magnesium salts of fatty acid. As calcium and magnesium salts of fatty acid does not dissolve in water, they will precipitate out as a white color precipitate. And after precipitating the soap, or after precipitating the fatty acid content in the soap, the solution is now left with dissolved sodium hydroxide. So therefore, if you filter out the precipitate, you will obtain a solution that will mainly contain the excess sodium hydroxide that was found in soap. And you can titrate this sodium hydroxide with the use of a strong acid like HCl with a known concentration in the presence of an indicator like phenolphthalein. And based on the titration, you can calculate the number of moles of HCl that was spent on the titration. With that, you can calculate the sodium hydroxide number of moles present in the entire solution. And based on that, you can find out how many moles of sodium hydroxide was found in a known mass of soap. So therefore, you can communicate the sodium hydroxide content as a percentage, or you can communicate the total mass of sodium hydroxide found in 1 bar of soap. So students, with that, we have now outlined a method to determine the sodium hydroxide content. We can now move on to the next step. To clear a household drainage pipe clogged with oil and fat clumps, specify the chemicals required for unclogging the pipe and describe the process involved. So students, if a household drainage pipe is clogged with oil and fat, what can we do to unclog it? So if it has oil and fat, then what will happen if you add sodium hydroxide? What will happen if you add sodium hydroxide? At that point, students, these oils and fats are basically triglycerides. Now, triglycerides will undergo alkaline hydrolysis if sodium hydroxide solution is added and will form soap. So, due to the formation of soap, this fat will dissolve in water and will unclog the drainage pipes. And apart from that, you can see soap that is formed is going to act as an emulsifier as well, because as you know, soap molecules do have their own washing action, where you can a part of the soap molecule dissolves in fat, the other part of the soap molecule dissolves in water. So therefore, remainder of the fat particles can be dissolved in water due to the formation of soap through this process. And then state how bleaching agent can be formed with the use of sodium hydroxide. Write the relevant chemical reactions. So you know the answer to this question. If you take sodium hydroxide solution and you bubble chlorine gas through it, you actually produce a bleaching agent. So we will take a look at these answers or questions separately and write down the answers for these questions. To clear a household drainage pipe clogged with oil and fat, specify the chemicals required for unclogging the drainage pipe. So students, at this point we can use NaOH. We can use potassium hydroxide as well. but the chemical that we can mainly use is a strong base like sodium hydroxide. At that point, you can write the oils and fat can undergo saponification, and make soap. And the other product will be glycerol. It is soluble in water, so it will not contribute to clogging the drainage pipe further. If it was an oil, yes, it would have contributed to clogging the drainage pipe, but glycerol, the other byproduct that is formed here, is not water insoluble. It is soluble in water, so therefore it will not contribute to clogging the drainage further. So apart from saponification process helping unclogging this drain, now first of all, well, let's figure out why saponification process will help unclogging this drain. So imagine you have a drain filled with fats and oils. So this is not getting dissolved by the water that is coming into contact with them. But if you add sodium hydroxide, what happens is these fats and oils will undergo alkaline medium hydrolysis, forming basically soap and glycerol. So this fat that is clogging the drain now is going to dissolve due to the saponification process, and therefore due to reacting and dissolving them, the clog will clear out. And another further assistance will come from the soap that is produced here. Now soap is able to wash away small oil or dirt particles because soap is able to dissolve the oil in water through the formation of micelles. Now we learned about micelle formation in the theory parts. So since the soap molecule has a hydrophilic head and a hydrophobic tail, the hydrophobic tail will get dissolved in the oil, especially tiny oil droplets, and then the hydrophilic head will be exposed to the exterior of the oil droplet, making it soluble in water. So we can say the soap produced will further assist the washing of fats and oils to unclog the drain. So these are the main points that we have to keep in mind. Now let's move on to the next part. State how a bleaching agent can be formed with the use of sodium hydroxide. Write the relevant chemical equations. So students, if you take a sodium hydroxide solution and bubble chlorine gas through it, right? If you bubble chlorine gas through it, at that point, a reaction that can take place will produce bleach. So we'll take a look at, now this is sodium hydroxide, and that is chlorine. So we'll take a dilute cold sodium hydroxide, and at that point with the dilute cold sodium hydroxide, if you react chlorine gas, it can turn to sodium chloride plus NaClO, which is our bleach, Along with that, water will also be formed. Along with that, water will also be formed. So this is the reaction that is taking place. You can see the equation is balanced. There are two oxygens here, two oxygens there, two hydrogens on either side, two sodiums on either side, and two chlorines on either side. So this is the reaction that takes place when it comes to formation of bleach. So this NaClO that is produced here is going to be acting as our bleaching agent or our bleach. So students, this is the reaction that we have to mention. And as the process you have to mention, you have to take cold dilute sodium hydroxide and you have to send chlorine gas through the solution to produce our bleach. Now we move on to the next question here. State how the below substances will react with sodium hydroxide and state the conditions required. So we have terylene, which is a polyester, we have nylon 66, we have aluminium, and we have sulfur. So we have to now mention the reactions that are taking place along with their conditions. So let's take a look at the first question, terylene. So terylene polyester has a structure like this. So now students, if you can observe over here, this terylene polyester, as the name suggests, is a polyester. That means these two monomers, or whatever the monomers that went into forming the polymer, are linked through ester bonds. You can see there's an ester bond over here. There is an ester bond over here, of course, because it's going to be connected to something like this that is over here. So this, what we have written is a repeating unit to the times n. That means this is the polymer. This is the formula for the polymer. So you can see another one of these repeating units will be present right adjacent to this section. That means this bond will extend to join to something similar to this part over here. And the same can be said about the bond that we have over here as well. This bond will extend to connect to a section that looks like this. So students, that means all of these are ester bonds. All of these are ester bonds. And in the presence of sodium hydroxide, what will happen to ester bonds? In the presence of sodium hydroxide, what will happen to ester bonds? We can say over here, when this is reacted in the presence of sodium hydroxide, aqueous NaOH, you will be producing these products. So we will write the products in blue color. Now we know when an ester is broken down with the use of sodium hydroxide, we call it alkaline medium hydrolysis. And when that happens, you produce carboxylic acid salts or carboxylate salts instead of the carboxylic acid directly. So we have this formed on one end. On the other end also you will have the same group formed. Apart from this product, we will also obtain a diol, which happens to be this.
So we have dioic acid. Now in this case, since we use alkaline medium hydrolysis, we don't have the acid form here, we have the anion form of the acid along with the sodium ions forming sodium salt of the acid, and we have a diol alcohol formed as well. So these are the products that you obtain when pterylene polyester is reacted with sodium hydroxide. Now let's move on to the next one. State how the below substance will react with sodium hydroxide. State the conditions that are required. So we have nylon 66. Now students, again this is a polymer. To be precise, this is known as a polyamide. So let's take a look at the nylon 66 structure. So we have NH and CH2 6, along with, again we have NH and H, C double bond O, CH2 4, C double bond O, extending this bond this way. So again this will be connected to a NH. So students, this is your nylon 66. So students, this is the structure of the polyester that we have been given, nylon 66. You can see between each of these amide bonds, actually first of all let's highlight the amide bonds that we have over here. So starting over here, very clearly we can see there is an amide bond here. So whenever carbon with a double bonded oxygen and nitrogen is forming a bond, that in this case is going to be our amide bonds. So even over here you will have an amide bond, and here as well you will have an amide bond. So students, when we react this with sodium hydroxide, we can carry out hydrolysis reaction, alkaline hydrolysis, and will produce the monomers that were used to produce this polymer. However, when it comes to the part that we have over here, the monomer will not properly be formed, because the monomer that we have used to produce this nylon 66 polymer is a dicarboxylic acid. However, we don't get the dicarboxylic acid produced when we are using our alkaline hydrolysis method. So instead we are getting a sodium salt of the carboxylic acids. So if you use sodium hydroxide, one of the products that is getting produced over here is a diamine. We have CH2 6 NH2, CH2 6 NH2, and here as well you have NH2. Now apart from that, you will have C, we will write it further to the right, we have C double bonded O, ONA. So when you write ONA, students, keep in mind we can understand that there is a negatively charged oxalate anion, carboxylate anion here, and positively charged sodium ion. So negatively charged carboxylate anion along with sodium 1 plus ion is usually written like this. But you may have noticed that sometimes we also indicate the charges on each ion like so that you have a better understanding of what type of attraction is observed here.
Right, students. So these are the two main products that is formed when nylon 6,6 is reacted with sodium hydroxide. Again, this is a alkaline medium hydrolysis that is taking place, and what we have over here are amide linkages or amide bonds, and these bonds can be broken in the presence of sodium hydroxide when we are carrying out a hydrolysis reaction. And if you do alkaline hydrolysis, these are going to be the products that are going to be formed. Keep in mind, when you carry out an acidic medium hydrolysis, the products are going to be different to these. Right, students? So let's move on to the next question. State how the substance will react with sodium hydroxide. So we have aluminium. Now, aluminium, when reacted with sodium hydroxide, it can produce aluminium or sodium aluminate and dissolve in excess sodium hydroxide. So we have to take aqueous sodium hydroxide and react it with aluminium and heat it. So we have to use aqueous sodium hydroxide, NaOH, aqueous, and you have to heat the system. Now, apart from that, students, you have to mention the balanced chemical equation. So when you're writing the balanced chemical equation, unlike the other reactions, we will have to add water to this reaction to balance the equation. So as a reactant, we will be adding water as well. And of products that are formed are, we have sodium aluminate, LO2, and hydrogen gas. So at this point, you will obtain the balanced chemical equation. So one of the easier ways to remember the balanced chemical equation for this reaction is all of these reactants and products will have a stoichiometric coefficient of 2 written in front of them, except for hydrogen. So we will have to add 2 in front of each of these, and then only when it comes to hydrogen, we'll be writing a 3. So at this point, this has to be balanced. So let's see if it is balanced. We have 2 sodiums on either side. We have 2 aluminiums on either side. And when it comes to number of hydrogens, we have 2 hydrogens here and we have 4 hydrogens here. Altogether 6 hydrogens. So when you take 3H2, 6 hydrogens are that requirement of having the same number of hydrogens on either side is now fulfilled. What about oxygen? There are 2 oxygens here and there are 2 oxygens here. Altogether 4 oxygens should be represented on the right hand side. So you can see there are 2 aluminate, that is sodium aluminate, that is formed. So therefore there are 4 oxygens there as well. So number of oxygens on either side is correct. So this is the equation for reacting aluminium with sodium hydroxide. And you will not be able to balance the equation without the use of water here. One important detail to remember. Now students, if you take a look at the fourth part, we are asked to show what happens when sulfur reacts with sodium hydroxide. So first, let's take, if you have excess sodium hydroxide, you have excess sodium hydroxide reacted with or heated with sulfur. So at that point, let's take a look at the reaction that is taking place. At that point, let's take a look at the reaction that is taking place. So students, we have excess sodium hydroxide. So NaOH reacting with sulfur will produce sodium sulfide. Sodium sulfide. And sodium sulfite, Na2SO3, sodium sulfite along with water. Now we have to balance this equation.
Now keep in mind, students, here you can see sulfur has turned into sulfide and sulfite. Sulfide and sulfite. So if you take a look at the oxidation numbers, now sulfur over here has an oxidation number of 0. So we will use a different color over here so that it is clear to us what is taking place. So the oxidation numbers will use a different color. So sulfur over here has oxidation number of 0 and sulfide over here has oxidation number of -2. And sulfite over here has oxidation number of +4. You can see there are 3 oxygens, each oxygen is -2, so -2 into 3 is -6. The overall charge is -2 here. So when you work the details out by find the sulfur's oxidation number, the answer you get to is 4. So if you are not familiar with balancing or trying to obtain oxidation numbers, we can quickly do that here. So we can directly take the sulfite ion and try to find the oxidation number of sulfur. This is X. You can see if you add the oxidation number of sulfur along with the oxidation numbers of oxygen, there are 3 oxygen atoms, each one is -2. When you add all of them together, it should be equal to 2 minus or -2. So when you solve this, you can see X minus 6 is equal to -2. That means X is equal to -2 plus 6. So therefore this is going to be +4. So the answer for the oxidation number of sulfur over here is +4. And we can see that when we are carrying out this reaction, sulfur is getting reduced to -2 and it is getting oxidized to +4 as well. So this is what is known as a disproportionation reaction. The same chemical species is undergoing both oxidation and reduction. So it's the same sulfur that is undergoing, or it is the same element here, sulfur, that is undergoing oxidation to +4 and reduction to -2. So when it is reducing, there is 2 electrons gained over here. So we will use a different color now. So there's 2 electrons gained over here per each sulfur atom. And when it comes to oxidation, we can see 4 electrons removed over here. So there's an involvement of 4 electrons here, or 4 electrons are removed over here. And when sulfur undergoes oxidation once, there are 4 electrons removed. That means when it is undergoing reduction, the number of electrons in both oxidation and reduction should be balanced. So that means if you need to have a balance between these 2 processes, since we have to have the electron number balance, we have to say that this reduction process should take place twice. The reduction has to happen twice, once when the oxidation process happens once. So that at that point the number of electrons in both sides will be the same. So oxidation releases 4 electrons, and to take all of those 4 electrons, the reduction process of sulfur going to become sulfur -2 should happen twice. So the reduction process should happen twice. So at that point, there should be 2 sodium sulfide produced. When 1 sulfite ion is produced, there should be 2 sulfide ions produced. So that is why we have to add a 2 in front of this number, because this process has to happen twice. So that means we have to have a 2 in front of this number. So altogether at this point, the number of sulfur that is found on the right hand side is 3. So therefore we can add a 3 in front of this sulfur. Now we can proceed to balance off the rest of the equation. You can see that there are 2 sodiums here and there are 4 sodiums here. Altogether 6 sodium can be found on the right hand side. So to get the same number of sodium on the left hand side, we'll have to add 6 here.
And afterwards, we can proceed to balance the oxygens and the hydrogens. So if you focus on the hydrogens, there are 6 hydrogens here. To balance the hydrogens over here, we'll have to add 3. So at that point, students, we can see the hydrogens are balanced and automatically the oxygen should be balanced. There are 3 oxygens here and 3 oxygens here, altogether 6 oxygens, and we have 6 oxygens here as well. So this is the equation. This is the equation, balanced equation for the reaction between sulfur and sodium hydroxide in aqueous medium when we have excess sodium hydroxide heated with sulfur. So what will happen if sulfur was in excess? So let's write NaOH plus excess sulfur. NaOH with excess sulfur. So at that point, students, due to actually this same process can take place, but the sulfur present in the medium can react with the sodium sulfite that we have produced and move on to produce Na2S2O3, sodium thiosulfate. Sodium thiosulfate can be produced. So at that point, the final reaction will change. So initially this reaction can happen and the excess sulfur that is present in the medium can react with the sodium sulfite that is now produced as a product, and this sodium sulfite and excess sulfur in the medium can react with one another to produce sodium thiosulfate. So we can write the same equation, but we have this underlying reaction happening due to the presence of excess sulfur. So there will be one sulfur added here. Along with that, the sodium sulfite here is now going to change to sodium thiosulfate. So the answer would be 6 NaOH reacting with 6 NaOH reacting with, altogether there was 3 sulfur here. Now we can see this process is also happening, so therefore it will be 4 sulfur. 4 sulfur turning into sodium sulfide and sodium thiosulfate. Na2S2O3. And apart from that, so when it comes to this number was 2, so it doesn't change. Apart from that, you will be forming the water that is present over here as well, 3H2O. So this is the final equation for the reaction between sodium hydroxide and excess sulfur. Sodium hydroxide and excess sulfur. Sodium hydroxide or excess sodium hydroxide and sulfur, the equation is this. This is excess sodium hydroxide. Over here what you have is excess sulfur. So students, you can have a look at both of the equations here so that you have a better understanding of what is going on. And with that, students, we can conclude the questions that were associated with the experiment number 41. In the experiment number 41, initially we looked at the theory parts revolving around preparation of soap or manufacturing of soap. We looked at the 4 main steps: saponification, removal of glycerol, purification, and finishing steps of manufacturing soap. And then we moved into the lab and actually conducted the experiment, and we saw how the soap is going to be produced through a saponification process. Now students, after that we came here into the classroom again and we were able to go over some questions that are revolving around this experiment number 41. By now, I hope you have obtained a good enough understanding about the theory parts and the type of questions that are asked of this saponification or soap manufacturing process. So therefore, students, with this, we can conclude our experiment here, and I will see you again in the next experiment.